dynamic package. And for that one, so there was one for the day 2 for simulation. Day 1, day 2, we do another simulation. And for the computer, we can still have today reserve the nodes until midnight. But one question I'd like to ask, do we still have interest today to continue like say yesterday after the regular session for the non-simulation in the after hours? That interest? Okay, that's great. So we can keep the reservation, now release to other general use. And today, so going to continue to have lectures. So just release a number of the acronym here: single column model, RM, MMF, and MXX, HES, Marine BGC. So hope this acronym itself are kind of intriguing. And those are special configuration of the models or some advanced development of the models. And that will shape the next generation of our model. So hopefully you remain interested. And after that one, we have post-processing workflow and practicum on additional code modification. And some of the code modification can extend that one to the normal simulation for after the session. Another thing I want to mention is for tomorrow's breakout. So tomorrow is a mostly practicum and question and answer session, and we'll break into 3 groups, likely put on the different room. So think about that one. We have atmosphere. So I heard yesterday have interest, like say, to do the nudging, and we have a specialized code with a hiccup program we're going to introduce, and then we'll introduce and work through the practicum with the offline land testbed. And another was the ocean and CIS, including the impact ocean, CIS, and impact analysis breakout. So think about that one, your interest, and towards the end of the day, we'll see the interest in each component group and plan the room and session accordingly. Thank you. So, and next, I will stop sharing here. We will start the actual lecture. So today's first lecture is going to be presented by Dr. Zheng on single column model and Doubly-Periodic configuration.
Good morning. Nice to see you here. My name is Zheng from Lawrence Livermore National Lab. This single column model and a doubly-periodic configuration are mainly developed by Peter Bogenschutz. He is out of town, so I'm glad to have this opportunity to introduce those configurations to you as a long-term user and the first few alpha user of DP-Screen. So those 2 configurations are maybe the simplest, the well-constrained configuration in a climate model. Because, for example, E3SM single column model, it just isolates a single column of the globe. You just let the local parameterized model physics calculated with the prescribed large-scale forcing. So there is no interaction between the local process with the prescribed large-scale forcing. The large-scale forcing is driven by intensive observation period IOP file. It can be designed from the observation or the theoretical forcing. Within this model, as you can see, we can determine what regime it will be through the large-scale forcing. Similarly, doubly-periodic screen, I put the full name of the screen here just in case you haven't get an idea for the screen. It's a storm resolving model developed by E3SM. It's also a single point cloud resolving model because it isolated a column of the globe. You can design the domain size. You can put the domain size as large as possible, but it just sends the same large scale forcing and the same location. You can determine the resolution by yourself for specific simulations, and the figure shows a cloud simulated within one simulation. Why we see it's very efficient configuration, because it only runs in like minutes within one single processor. You will finish up one single column model. Similarly for DP-Screen, although you know the global cloud resolving model is, it's hard to imagine you can run it by yourself. but you can use the debug node on NERSC to run DP-Scream as many as you want. The right figure shows a snapshot of DP-Scream simulation. You see the domain is very large. It's over 1,000 kilometer times 1,000 kilometer. But can you guess, is it using the same longitude and latitude over the 1,000 kilometers? Or they will sense the different longitude and latitude? It's a guess.
Probably the same.
Yes, I said it's a single point. And also they sense the same prescribed large scale forcing. Do you think, but maybe it's very obvious, it will develop a tropical, even with those single point setting, the DP-Scream can develop a tropical cyclone if you have a favorable large scale environment and you consider Coriolis force. I will show you the movie if we have time. For such efficient configurations, what we can use for model developer and researcher, firstly, it can make the debugging the model very efficiently. We don't have to wait for nodes assignment and take time to run the simulation and to analyze the interaction between the large scale forcing and the local physics. Since if we are debugging the model parameterization scheme, the second items, whenever we want to develop a new parameterization implementing a global model, or you want to upgrade the parameterization, you'd better start from the single count model. So you will know under certain large scale forcing if it's reasonable. The third aspect will be used to evaluate model bias and deficiencies with some observational reference. The lastly is recently emerged usage is performing perturbed parameters for machine learning purpose. I hope the first two slides already get your attention to this configuration you want to try. And if you want to start it, there is a link. It's well maintained. You have a lot of details you can click now. And when you click it, you will see similar thing like the figures showing here. You choose if you want to run single column model or you want to run DP-Scream. This is the example for the single column model. And here you have three axes. One is script and the instruction for you to run a model. It's very easy, especially on NERSC. And then you can pick the case library. As I said, you need to prescribe the large scale forcing for this simulation. If you want to understand the parameterization's impact on marine boundary layer clouds, for example, you can pick the case. Or you want to understand deep convections case, you pick the appropriate case from the library. When you finish up the simulation, you can run a diagnostic package to give you a set of results to make sure it looks reasonable. If you click the case library, you see there are so many libraries. The IOP files from the case library supports both single count model and the DP-Scream. In the case library, you also see some short description, like this case is good for what type of purpose, and it has a reference data, like when you run a simulation, you can compare your output with testbed reference data to make sure your setting is correct. So far, we have provided more than 28 cases, and the case number is keep growing from the contribution of different projects. For each case, we have a well-documented run script. You just need to make a revision on the run script, so you will be able to track what you have done to this case. Here is a closer look of the case library. We have several different perspectives. Like we heavily used our boundary layer case, from a marine stratocumulus case to trade-cumulus case and cloud transition case, continental clouds, or even stable boundary layer clouds. So you pick what case you want to use. Those cases are mainly like a few days to maybe a couple of weeks But we have continuous forcing that you can run long-term with the case setup for SDP and Darwin and Go Amazon. That's the long-term simulations. You can get some climatologies. For deep convection case, there are several cases, including the theoretic radiative convective equilibrium forcing you can run. Meanwhile, the threat team keep contributing new cases for cold air outbreaks from combo and cloud transitions from magic and clear boundary layer case and the shallow to deep convection case. If you track this closely, you will see the case will growing, and we'll welcome you to give feedback on certain case or what do you need. Like if you have any special need, want to add it, we will be able to find out the forcing to meet your research need. So now I want to show you some examples we have been done use single column model and DP screen. Firstly, as I said, when we implement a new physics into a global model, the first step is always using single column model simulation to test, to do the debug. Like the right figure shows the real examples from Peter Borgenschut's implementation of the new turbulence scheme shock to E3SM. When he firstly implemented this scheme into shock, he ran a marine strand cumulus case called DICOM 1 case, and quickly he noticed there is something wrong. The boundary layer didn't build up and it's too shallow. That means the original implementation is not physical and it need to be debugged. He did intensive debugging and figure out what's going on, and the debugged scheme looks much more realistic. And he figured out that's these things happened so often, so common in the parameterization scheme implementation. With this case, you compare with the default parameterization simulations, you will know the sensitivity of your new parameterization. And it also gives you some confidence it will be ready to run in global, especially if you run so many cases from shallow convection to deep convection to continuous forcing, it looks reasonable. And then you put it in the global simulation, that will be more confident. Like what if you skip a single column model configuration, you go to the global model, when you see this, you cannot explain why it happened. Is it a parameterization problem or it's large scale forcing? Like the general circulation has some biases. And with the single column model, that's easier to debug. Another way was after you implement all the parameterizations in the model, you want to check the interactions across the parameterizations, and also you want to check different processes. And here is two examples. We used a single column model to evaluate clouds and the cloud physics and the turbulence. The top panel shows the magic. It's an arm field campaign from stratocumulus to cumulus transition case. We use observation and a single column model with NAGIT simulations, check and then identify the microphysics time step is too long, and the precipitation fraction method is unrealistic in V1. So we made suggestions, and later for P3, in current V3, they updated the precipitation fraction method without using this unrealistic one. The second example is using a still marine boundary layer clouds in the Azores. We identified some artificial cloud oscillations in the simulation. With global simulation, it's hard to interpret or explain this oscillation. So we conducted a single column case with the forcing from this location, and we uncovered the problem is from the coupling between turbulence and microphysics. Whenever they have coupling, they cause some too strong evaporation cooling and kill the boundary layer. When we adjust the coupling, the oscillation disappeared. And there are so many other examples with single column models. And now we also use DP screen to evaluate the cloud at the process levels. And I won't show that result here. But for DP Scream, we want to see some unique applications. It is horizontal resolution sensitivity. As I mentioned, we can design the domain size and the resolution for DP Scream. And with this, it gives us the opportunity to check if this model is scale sensitive or scale insensitive. Firstly, when they implement the Scream, they use the same DICOM 1 case and other many cases showing in this paper, Peter Bogenschul's paper, that he did a resolution from 5 kilometers to 100 meters and did a simulation. They see it's very consistent. The spread among those resolutions is less than the LES members, and it's very consistent with observation results. So we got a conclusion that Scream is relatively scale insensitive, and the simulation are in good agreement with observation. Here is only one example. You will see more cases from this paper. Another application for DP Scream is, although it's single point simulation, it still can replicate the cloud biases shown in the global simulation. When we have a Scream V1, they show that it has struggles to simulate the transition from stratocumulus to cumulus. Especially for shallow cumulus, it's too shallow and it's too stable like stratocumulus. Inspired by that, we conducted a DP Scream case with shallow convection over SDP. Compared with observation and LES, we do see the DP Scream with 3 kilometer resolution. The shallow convection cannot build up deeper, and the cloud fraction is too low compared to observation, but still too high compared to LES. When we increase the resolution, the cloud can go deeper and more similar to LES. This gave us a clue that when we increase the resolution in Scream, the shallow cumulus cloud will be improved. Here is the most famous example in the DP Scream. Thanks, Chris Terwright, courtesy for the figures. And actually, the DP Scream study was conducted by Chris Terwright. When the Scream global simulations we see in the maritime tropics, they have those scattered and very small, smaller than observed precipitation clusters you showing in the figures, scattered without any aggregation. Compared to observation, the size is too small, just like the popcorn. This is the most serious bias we identify in the model with a version 0. So they conducted DP Scream and they noticed, they confirmed that the DP Scream can reproduce those problems, like those too small intense precipitations. With DP Scream, they can efficiently conduct a lot of sensitivity tests from all aspects, and then they uncover the issue still in the coupling between turbulence and the precipitation. Improve the coupling between turbulence and precipitation, they reduce the popcorn issue by half. Although it's still ongoing work, but that demonstrates the DP Scream can be a very efficient platform for model bias identification and improvement. So I think I have enough time now. All those things just want to convince you that single column model and the DP Scream configuration is very efficient configuration to know the model, to do debugging evaluation, and do some research, well-constrained research for local physics. If you want to try, there is the one link that can provide you all the information you want. Please be free to ask any questions here, or later on you can contact Peter Bogenschul through the email. Do we still have time? Yes, please go ahead. Yeah.
Thanks for the talk. I'm curious, aside from the default cases, is there any tool or script provided for the user to create their own large-scale forcings for their own cases?
That's advanced users. Like maybe I can do some my own large-scale forcing generation, but they have so many steps. I think model has a configuration that can output like a local large-scale forcing for you to do single column model debugging. Like if you run global simulation, you notice some place has issue, you can set up the configuration to get the IOP file from the global simulation, use that to drive your single column. But that part is a little bit complicated. It won't cover by this tutorial. You can contact Peter. There are several steps for the post-processing to get the forcing ready. But yeah, the function is there. Like you can design your own IOP for your own case.
Is there an equivalent for the ocean, like a column ocean model?
Mark, is Mark here? Maybe later on, yeah, ask Mark.
Okay.
Yeah.
There's a column ice pack model.
Ice pack.
And the land model will also some kind of similar design of single column. Ocean, I'm not sure.
Ocean better, let's step up.
But maybe ocean has the circulation maybe is more leading factor for the like a single column model is more for the local physics.
Yeah,
And
I
you
was thinking for
prescribe that.
BGC testing.
Oh,
So that, like, if I had a column model of the ocean, it would be really helpful for debugging the BGC.
I see. Yeah, that's legit.
Jess,
Yes.
thank you for the overview. Couldn't help but notice that a lot of the field campaigns that were informing your IOP development
Mhm.
were some years to almost some decades.
Mm-hmm.
Are there anything that observationalists can be doing now while we are designing current and future IOPs to better align our observables and our spatially and our observing strategies so that they can better inform and more efficiently drive either consensus on new cases to follow or the implementation of those cases?
Actually, this is an ongoing active topic in ASR, the ARM ASR community. We want to design the future field campaign to have the area coverage like to meet the DP screen need. For single column model, it's okay to have a like a homogeneous observation, but for DP screen, as you see, we already can cover the cloud resolving field, the heterogeneous cloud field. So the scanning observation will be very useful. Like that's just one perspective. What I want to see is there is active ongoing topics to try to initiate the discussion to make the future field campaign can generate observations, meet the model need. And we have continuous forcing team in ARM team. They generate a continuous forcing for each field campaign. That can be a good candidate for large scale forcing. But for observations, actually we need more observation reference to evaluate the model and understand the model behaviors. That part we need more like in-depth discussion. We don't know what the observation's capacity modeling perspective, but we can provide our need. Like we wanted the cloud water distribution or maybe like a cloud masks over the whole area, something like that. And so that will be an ongoing work. We can talk offline to build up. Like the new cases for combo, we want to cover some cover better observation for this case, like a cloud face partitioning. That's not included in any previous older field campaign. Yeah, so we want to take into the most advanced observations results into this case library. Yeah. Yes, please.
So for the single column model, which version of E3SM is it running, or is this a configuration that is you can do with V2, with V3? Will you be able to do V4 as soon as it comes out?
Yeah, in theory, it should be running with V1, V2, V3. It's a maintained configuration. But for before the model is phrased, officially released, there might be some problems in like a technical issue, but it's running with V1 and V2, and we're actively using single column model to do our research. And if you have any technical issues when you're trying to run it, just contact Peter or me. And I'm an intensive user of the single column model.
Yeah, by the way, and just recent week, Peter Bogenschutz will updated this some of the change, and essentially you can also work with the current version of the V3.
I don't know if you're aware of this, or maybe it's a question for Chris, but in the case of radiative convective equilibrium, when you don't have large scale forcing and the domain is large enough, do you get self-aggregation of convection, or is it also popcorn?
Depends on the Coriolis forcing. I think like this case, it aggregate as you have very strong.
Like F plane with large enough domain, you get a hurricane.
Yeah, yes.
I wonder if without rotation, if you also get a cluster or.
That's I need to double check with Peter, because it's active research area. At the very beginning, we couldn't get it just like popcorn, but as I mentioned, we did they did a lot of model development. It's getting better, so the cluster gets better, like aggregation is better. I don't know the current stage. And actually, when since you mentioned about the RCE, they are developing another configuration that it's not a single point anymore, so they can sense the SST gradients in DP screen. In that way, you can simulate Walker circulations and everything. So it's very actively this area is actively developed. So maybe it's better to check with Peter, or maybe we can have an offline discussion to see the latest stage. And so far, I showed it's well-established area. So
Joy, actually, Peter showed me the animation yesterday. It does aggregate in RC.
okay. Yeah, so that's really.
Thank you.
Okay, I think I run out of time.
Okay, oh, time is good. So any more questions?
Okay, please.
I was just curious how much of aerosol chemistry is included in the current version of SCM or screen?
Yeah, that's a good question. Aerosol is super important. The screen so far for the global model, it used the prescribed aerosols. So in DP screen and single column model, they share the same capacity that you can prescribe the cloud droplet and ice droplet, and also you can prescribe the aerosol, you use climate. But that part will need a further development to make it more sophisticated. And you can prescribe, you can perturb aerosols, but it's not interactive aerosol procedure, yeah. Maybe, so this is the things I mentioned, the question mentioned with single point forcing, we can see the convection start generate and you get very intense. Oh, I wouldn't say it's very intense because I don't see the sea level pressure or wind speed, but the precipitation looks very like a tropical cyclone to me. Yeah, I hope Peter shared the animation of the general RCE with me, but I don't have that. Maybe later can request it. Yes, please go ahead.
Hi, sorry if I missed this, but if this is a point simulation, how do you get like spatial characteristics?
They set just like a LES, like a classic LES. They use one location, but you use X and Y to specify the grades within the domain. But they all sense the same longitude and latitude. Whenever they use the surface condition or they use Coriolis, otherwise they just split it with X and Y. So it calculates like a traditional LES, but the resolution is about 3 kilometers. And the parameterizations and physics are not the same as traditional LES. So they have Doubly-Periodic condition. Whenever the things move out from the boundary, they move back from the other side. So it's a closed system. And the imposed large scale forcing everywhere are the same, like a large scale U and V or tendency. So everywhere is the same every time steps. But the grade bar, like the equation will calculate the tendency for each grades within the domain, the whole domain. Is that clear, or I make you more confused?
And yeah, so thank you, Zheng, for the nice presentation. And thanks for the nice question from the audience as well. And before I switch to the next speaker, I just give a quick comment for the run script. For the past 2 days, we recommend using a single run script to consolidate everything into one and then run control the simulation. And in the same spirit, the single column model also put everything into a single run script for different cases. But because of each case, it involves different settings, including some prescribed aerosol and other large scale forcing or even some physical parameters. So each case different. So those are not consolidated. So therefore, the run script template is different from the run script we have been using. But you can follow the wiki page and download. It's going to be very quick, out of the box, make some change to the code path and next machine and be ready to go. So you can do the test. So our next lecture is on regional refined model. That will be provided by Dr. Tang, also from Lawrence Livermore National Lab. Thank you, Wuyin.
Should I always stay here or I can move?
You can move.
All right,
We have recording, so I should stay
Yeah.
closer to this.
all right, so I'll just give a very high-level overview on the regional refined model, and sometimes it's also called a various resolution model. So you can see the grids here on the top. That shows the atmospheric grids for E3SM V2 North America regional refined model. So and then on the bottom, that's the ocean grids. So I'll talk about later, but just give you a overall what the mesh looks like, since you just heard the DB screen lecture. And then, so why do we need RM? So the major reason is that when we always wanted the model to be a higher resolution, but if you increase the resolution everywhere, the computational cost normally would become unaffordable at some point. So that's why we have this RM application. And then as you can see from the grids showed on the last page, the fine resolution portion actually normally would determine the overall cost for the whole RM. And then we normally choose something between 10 to 20% of the uniform high resolution. So on the table here, I gave the throughput and the computational cost for E3SM V1 atmospheric model in V1. So it's not only consider how much the allocation the model would cost, it's also a consideration of how fast in workload time. Since I believe some of you are among here are a PhD student, so you certainly don't want those simulations taken forever. You wanted to finish before you write your thesis, right? So, and then for the atmospheric component, we have this tool to complement with other efficient tools. So like single column model and DB screen, Xue just covered. So some differences between that is in RM, you have topography, orographic effects, latency contrast, and then the large scale circulation would feedback to the high res region. So it's two-way coupling. And then the forcing is not idealized. So it is a global model. It's just the resolution is higher in some places than other places. And then more importantly, the regional refined capability actually developed for other major component in E3SM, because not only atmospheric model has a subgrid scale unresolved processes in other component like ocean, eddy activities, and then for ice streams, and also land surface model, like land surface types. So they all requires higher resolution. So starting in E3SM v2, all the major components can do RM. So that's a very very good advancement. And then how to build a RM case? It's actually fairly simple. You just use the same create new case command as you used in the uniform grids, and then change those resolution names. So I listed three there. Those are the three for V1, V2, and the ongoing work of V3. I don't recommend you remember those awesome long names. And then once you created the case, then how are you going to run it, right? So some parameters can be tricky, because the physics parameters can be spatial as well as temporal specific. So maybe raise your hand here. If you were there to run the simulation, you have low res, high res domains. So which set of parameters you are going to choose? Low resolution ones? Okay, no. High resolution. All right, okay. So I see most of you choose somewhere in between. But unfortunately, we don't have that option. Oftentimes, those parameters are just a scatter. We want it to be maybe more clever in the future, but not there yet. So this is what we do normally in E3SM v1 and also in most previous RM applications. So when possible, if we have a high-res configuration, we apply that. And then trying to mimic the high-res domain in the RM as much as possible to the uniform high-res. And then in this case, we had to change some of the parameters from the default. So for club, and then dipole, and then deep convection. So, but sometimes if you don't have a uniform high resolution model in place, then, and also it takes a lot of effort to tune a different set of resolution, the high res, beyond the low resolution model. Then I'll cover more later, but let me give you an example very quickly. For that, in V1 case, this is the summertime precipitation. So the domain shows on the left, and then this is the high resolution and the low and RM differences over the high res domain. So if it's not dotted, means the difference are not significantly statistically different. So the results basically highlight that in V1, so EAM V1, our model can reproduce the high resolution pattern. But then I want to note here, when people compare low res versus high res, normally would think the bias might be smaller. But in this case, we just want to highlight that RM has the capability to reproduce or mimic what the uniform high res shows in the climate, not necessarily better than the low resolution results. And then in E3SM v2, we decided because we already put a lot of effort before in developing the high resolution E3SM v1. So and then in V2, we wanted to try something different. So we will use this North America RM as our high resolution configuration for V2. And then it's probably the first of its kind application of RM in all major components, which delivered the CMIP6 production runs. Which is very different from only for some specific scientific applications for some cases or for limited period. Because to do that, we'll need to do long time coupled system spin up, as well as the radiative adjustment has to be in equilibrium at the top of the atmosphere. So that's a much, to me, it's a much higher requirement. So then the key achievement for V2 now is that we improve the climate at a refined mesh without sacrificing too much of the fidelity of a low resolution mesh. I will show more results later. And then we achieve this by applying this hybrid time step method. So for the dipole in the atmosphere model, we use the high resolution configuration. But for the physics, we use the low resolution configuration. Of course, this comes with some benefits and disadvantages. So the benefit is that by applying this hybrid time step, we don't need to retune the model beyond what we have for the low resolution model. So the parameters would be exactly the same for the physics. And on the downside is that the time truncation error would be larger at the 25 kilometer grids. And then the model runs very efficient. So 12 simulation year per day on this crossless machine. This is the throughput, even better than the low resolution V1 model. So with that throughput, we can certainly do production run. And then look at the global results first. On the left, you probably already seen those plots in previous lectures. So looking at the global metrics, the low resolution and the North America configuration are very similar. For some variables at some seasons, we see slight improvement of the RM compared to low res, which is expected based on our hybrid time step design. And then on the right-hand side, I showed that the two model configurations have similar climate sensitivity as well as feedbacks. So this is all good. This is the global climate we would want it. And then for the high resolution domain, then I'll give more results and then show some examples in each component. And then on the left, that's the wintertime precipitation. So RM can obviously resolve more finer structures because the topography is finer. And then on the right-hand side, that's the biases. I'm showing the shortwave cloud forcing, but that's the marine stratocumulus bias, which is a hard issue for climate modeling for many years. And then with the fully coupled RM, we actually substantially reduced the low cloud bias in this region. This is off coast California. And then we cannot do that only in refined atmospheric model. Those four configurations is a combination of low res and high res in both atmosphere and the ocean. So swapping them, so there are 4 combinations. The SST bias would be smaller if you refining only one component, but then when you refine both, then you get the best results as shown on this figure. So this really highlights the strengths of the capability to refine in multiple components than only one. And then another hard to solve issue is the high latitude mixed phase clouds. So in this example, we have the liquid and ice cloud cover. So over Alaska and near the Greenland, you can see for both the liquid and ice clouds, RM is better than low res. Over land is mostly because the topography is better. And then near Greenland is because the better sea and the ice and the atmosphere interactions. Because in all 3 components, we have the refined mesh. And then one example on the right, that's for the land model, shows the snow water equivalent. So this is for winter, then the snowpack climatology is better represented for the spatial variability. And then for the river runoff, actually the first time I saw those river routes on the plots, I was surprised. in the low resolution model, that's the I believe it's ½ degree, perhaps maybe I'm wrong, but that's what the river used in the low resolution compared to the 8th degree. So in the low resolution, some of the river actually are disconnected at that resolution. And then compare the river gauge geo-referencing information of stream flow on the right. This is plotted on log scale. So the improvement doesn't show as dramatic as showing on the linear scale, but still we see some improvement because the better topography improves the river model performance in terms of the routing. And then in the ocean, so we see the algae activities are very obviously better. And then near the Labrador and the Bermuda currents show on those circles, those are hard to resolve, but resolved well in the RM configuration. And another one is for the Gulf Stream, near the red dots, the currents actually is separated from the coastal region very nicely, which you don't see in the smeared out low resolution results. And similarly for the ocean current velocity at this transaction at OS NAP, so the RM is much similar than the low res compared to observations. So then have those examples. Then one more is for the sea ice observation on the left, and then standard. So low resolution results in the middle, and then RM results on the right. So the sea ice concentration is improved over the Labrador Sea, which is important to reduce the AMOC bias. But we have some aspect getting worse. The sea ice thickness shown on the bottom is worse in this configuration, but then the ocean and sea ice group made some new changes after this and then can be improved in V 2.1 version. So the results I'm showing here is from V 02, or no, 2.0, which corresponds to the maintenance branch 2.0. And then, so some ongoing work for V3 now, then we have this trigrid mesh, so different from the bigrid, meaning atmosphere and the land are on the same grid. So in V3, atmosphere and the land will be on different meshes. So we'll keep the atmospheric model grids the same as the V2. And then for land and the river, we'll use the same quarter degree mesh as the high resolution. And then the ocean and the sea ice, the same as the low resolution V3, which is a uniform 30 kilometer grids. It's already finer than the V2 low res. And then we'll try new time step strategy to take more advantage of the high resolution dynamics. And then with some retuning. This is ongoing work, so I don't have results to show you. But we hope to improve the model further and learn something new. And then some even more excited work, apparently for the RM, we can leverage the non-hydrostatic dipole to push the refined resolution to a kilometer scale. So on the left, that's one paper just published yesterday. So over California, the whole California region is covered by 3 kilometer grids, same as the screen resolution, which will be given, I believe, at 10 or so, one talk covered by Peter Caldwell. And then outside gradually decreasing to 100 kilometers. So in this paper, it's applied to simulate future climate projections. And then on the figures, you can see the topography plotted here. At 100 kilometers, we don't actually see a central valley. And then at 25 kilometers, we started to resolve some of it. And then it is at 3 kilometers, those fine topography structure show up. So, and then on the right-hand side, that's a work in review led by Peter Bogenschutz for the atmospheric river application. So it shows that the size of the refined domain, as well as the resolution of the refined portion. In this study, he even pushed it to below 1 kilometer, about 800 meters or so. And then to simulate atmospheric river for different types. And then lastly, someone asked about chemistry and aerosols. So if we turn on interactive chemistry and aerosol, then we can simulate wildfires. So same RM configuration for the California, and then this is animation created by my colleague Xiang He for the 2020 creek fire case. This is a fire case, very dramatic, and it's known to generated pyrocumulonimbus, pyro-CB events in 2020. So we can capture many of those fine features of the aerosol distribution. So, okay, so then I'll stop here with those links with more information and where to find our V2 production run data to download. And then if you have questions, then that's my email. Okay.
So those high resolution RRM runs are still on CPU, right?
Yes.
You have near-term plans for the GPU implementation?
We haven't done that, but once the C++ version is there, we can certainly run it on GPU. So yeah, it doesn't depend on the So the screen team first support the uniform grids and now have the RM capability built up, I believe. So yeah. So the throughput would be even better. Yeah.
Higher and higher resolutions.
And we can also add more physics, make the model more computationally expensive.
Especially the new computers are all transition to GPU, so it's difficult to also find CPU allocations. So you know,
Yes.
Move to GPU side. So
Yeah.
GPU.
And also at that point, how you are going to design your RM mesh because right now is depending on how many cores we have, the atmospheric dipole can at most run one spectral element on one core. And then for GPUs, if you don't have that many like element, then you may not be able to fully utilize it. So yeah, but yeah.
You go to slide 12, where you have the CS. So I see, yeah, so is that also configured under North American RRM?
Yes.
Okay, so I'm wondering, will there be another version for Arctic region or like a refined resolution for Arctic region?
So let me bring up the mesh first. So that's the atmosphere and the ocean mesh in those figures. We do have a atmospheric RM mesh over North Pole.
Okay.
But I'm not sure, but in this case, the North Pole ocean are already at 14 kilometers. So the blue means the resolution is higher.
Okay.
So yeah, can swap out and then.
Okay, thanks.
Yeah.
But there is an Arctic refined setup. Like, is Darren here? So there's a whole Arctic refined setup that's 10 to 60 kilometer.
Yeah.
So that, yeah, if you're doing Arctic stuff, that's probably
Right.
together.
Okay.
Thanks for the talk. I have a question regarding to the physics across different scales. And if I remember correctly, we're using different model physics combination at different resolution grid.
For RM, no. It's the same combination. That's why this, whether or not need retuning has to be considered.
Yeah, so because for those mesh with very resolution, one approach is to make the parameterization scale well. I'm wonder whether this is something that will be considered in E3SM. Mesh.
Yeah, we would very much like that. If some scale where parameterizations are available, then we would be very glad to implement that. And then, but that's also a question about regarding on which scales.
Yeah,
because right now,
sorry, I see one of the slides that this you mentioned like latest work have the finest resolution on at 3 kilometers.
yes.
So that's like a huge change from quarter two.
So in those ones, like what goes into this animation is that we turn off the deep convection skin. So it's off everywhere globally. And then outside the domain, the coarser domain, we apply the nudging. Yeah. So yeah, I guess what I want to say is that you need to know what exact configuration and goes into those simulations, and then to interpret the results correctly. So there are some limitations we know, and some of those might be achieved by next talk, like applying the MMF scheme.
How hard is it to design your own regional refined grid?
So when you first time do it, it's normally harder. And then once you gone through it, and then since if you change the resolution at different locations, you might run into so a few points. So one, you might run into new issues. That's just how model development is, right? If you try something new, you might be surprised by something. And second is that now we have a much better stream flow to build up those configurations to support new resolution. So when I first tried it, it didn't take me so long because those tools and the documentations there, and there are others I can ask. And then, but in terms of designing that, actually, if you mean because it takes a lot of effort to actually see the final results like this, you have to invest effort ahead of time. But then once the simulation looks not so good or not what we wanted, you go back and modify it. So has to consider a balance. So normally my approach would be make it under the constraint of the computational resources, make it as bigger as possible for the high-res domain. So in this case, I designed the California RM to have similar columns as the V2 now. So in that case, I have some references to compare for the computational efficiency. So the model cost mainly from the shortening time step. Yeah. Okay.
Thank you for the talk. I noticed that for the V1 RLM, the parameter table, the cloud technique time step is actually 3, so it's smaller than the default steps in low resolution. Could you talk more about the reason?
So these are the parameter sets used in the V1 high resolution model. So for V1, we have a 25 kilometer uniform configuration. So that's actually, I believe this tuning Wuyin or the Carpenter group made this change to that's for the sub time stepping, right? So yeah. Yeah, we can talk offline. Yeah, that's yeah, when tuning the model, you have multiple considerations. So yeah, in the interest of time. So yeah. Okay.
Thank you, Chi. Excellent talk. And you just showed that. Yeah, you just show unlimited application potential with the regional refinement for different regions, different topic areas. And just like the question asked, like how to generate the RM mesh is a challenge, but the basic procedures are documented and consider some level of the streamline, but encouraged to use and feedback to us and continue to improve. So the next lecture is by Dr. Walter Hanna from Lawrence Livermore.
Okay. Okay, so I'm going to talk about the multi-scale modeling framework in E3SM. Some of you may know this as super parameterization. That was kind of a popular term, but I decided I don't like it, so I switched to this one. And this picture I've got here, do I have a mouse here? Yeah. Okay, so this picture here is something I made using actual data from the model that depicts what the MMF actually looks like. I feel like it's a good way to introduce it. So what you see on the surface there is I've colored the precipitation that's falling at the surface, and then I visualized this embedded CRM, which is what we use to replace the convective parameterizations. And so that's the basic idea. You want to get away from the assumptions you make in traditional parameterizations and explicitly simulate convection instead, and boundary layer mixing and cloud radiative feedbacks and other things. So one way you can think about this is kind of an alternative way of enhancing the scale, the scales that you represent in the model. You could take a low res traditional model and you could enhance the resolution everywhere, keep the parameterizations and retune them, and you've effectively changed what scales you can represent. Alternatively, you can leave the global grid the same and add this CRM that covers a different range of scales. And one of the advantages of this is that, well, if you run this on CPUs, both of these strategies end up being about the same, like going to a 25-kilometer global mesh or putting the CRM in, you get about the same speed. But because the CRM is separate from the GCM, it's perfect for leveraging GPUs because there's no communication between the individual CRMs. So it works really well. It's kind of an ideal case for the GPU. Every time step, you send a bunch of information to the GPU and it sends it back. And there's just like a lot of work that is concentrated on the GPU. Kind of the original motivation for why the MMF was developed like over 20 years ago now, is that it's this middle ground between the gold standard of a global cloud resolving model that we all want to work with and the traditional parameterized model that we all kind of have to work with. And so the trade-off here is that you get explicitly resolved convection, but you can still run 100-year simulations. But the other thing that I think is maybe even more important is that it's just a different approach to modeling these processes and how they interact. So in terms of like cloud radiative interactions, the radiation actually sees the clouds, whereas the parameterized convection are kind of invisible to the radiation scheme. And similar, yeah, the way that microphysics interacts with the updrafts and aerosols interact with the microphysics within the updrafts, all of that's different from a traditional model. So since this is a tutorial, I figured I'd go over how you actually run it. It's very, very simple. It's just a change in comp set. So, oh, my slide got really messed up here, didn't it? Well, this was supposed to be a very nicely spaced and organized list. But anyway, there's a bunch of comp sets here that are already available. These like F2010, F20TR, so these are prescribed present day SSTs, fully coupled configurations, Aquaplane, RCE, single column model. And so I have an example line here at the bottom. In your create new case line, you just use one of these comp sets and it should run out of the box. But additionally, there's a bunch of kind of MMF specific things you can change, like you can make the CRM bigger or change the spacing, turn on various features. Some of these have to be set in the XML file. So here's an example where I'm making the CRM a lot bigger than it is by default. And then there are some things that are only available through the name list. Like if you wanted to turn the CRM 2D or 3D to be oriented a certain way. If you're not convinced that the MMF is useful, I figured I have this backlog of experiment ideas that I just don't have time to get to. And I figured I'd just put them out there in case anyone wants to steal them. And these are things that I think are particularly valuable because they're things you can't quite get at with a traditional model. So yeah, one thing a colleague gave me years ago, we were talking about the MJO. I'm sure everybody knows what the MJO is, right? Do I have to explain that? I hope not. Okay, I'm going to assume you guys all know what that is. But yeah, so yeah, you can change the ice fall speed. I mean, you can do this in any model, right? This is usually a parameter. But the MMF typically always gets a reasonable MJO. So it kind of gives you a nice test bed to think about microphysical impacts on these larger features. The other one, in regards to cheese talk, is that I think the MMF, I have had this idea for a long time, that the MMF is naturally scale aware. And that when you change the external mesh, like the global mesh, the CRM is going to have the same behavior no matter what. So it could be the ideal case for a free running RRM where you don't have to use any nudging to do maybe climate projection with refinement. The other one, we've done some, the marine stratocumulus is always a problem. And one nice thing you can do with the MMF is you can kind of brute force make this clouds better by kind of hyper resolving the inversion layer. and inside the CRM. So you get these great, beautiful low cloud decks. It costs a lot, but it's doable. And then the last thing is cloud scale Coriolis effects. You could turn on the Coriolis effects inside the CRM. So the non-traditional terms where you're torquing the zonal momentum into the vertical and vice versa. You can experiment with that inside the CRM. So none of these things you can do quite in the same way in a traditional GCM. So moving on just to show some results of some recent-ish work that I did last year with the fully coupled MMF. This is a historical temperature record. And it took me a long time to get all these results because I basically a team of one plus a few other guys. I had to tune the model and then do all these simulations. And so a lot of these are not, they're not done in the conventional way that you'd see in kind of the CMIP archive. In this case, I started the model in 1950. I did a bunch of kind of spin up and tuning in the 1950 conditions. And the blue line here is the MMF, and the red line is E3SM v2. And you can see there's this kind of delayed warming due to the aerosol feedback issue, which somebody's probably mentioned. Now the MMF has prescribed aerosol, so I avoid that problem entirely. But I was legitimately surprised that I got the warming here in the historical period so well. I didn't expect that, especially because I didn't tune it using anything more than like 3-month runs. Normally you run like 500 years, 100 years or something like that. And you want to see how the whole system is evolving, but I couldn't afford that. And down here at the bottom here, I've got kind of a summary of the computational performance. And these are this is a bit apples and oranges because the MMF is running on GPU nodes and the regular model is running on CPU nodes. But to the extent that they are comparable node to node, I'm using much more nodes and I'm getting less throughput. But the point I want to drive home here is that this is reasonable if you want to run 100 years. You know, without the GPUs, the throughput would be like under one, like maybe half a year per day, maybe 0.1, depending on how many nodes you can afford. So the GPU is really what pushes this into the terrain of being a usable climate model. Just quickly touch on the biases here. On the left, I've got the MMF historical, I think this is 1950 to 2014. And then I've got the AMIP or the E3SM v2 ensemble on the right, and then the bias with respect to observations. And you'll notice that in some ways the biases are very similar magnitudes. There are some places where the biases are much worse, especially over the Amazon. The MMF does really bad. It's always really dry there for some reason that we've never been able to figure out. But then some of them are very consistent, like over the Himalayas, the warm pool, the Atlantic ITCZ, the biases are comparable. Hopefully somebody showed a Wheeler-Collattis diagram, so I don't have to explain that. Okay, cool. Yeah, so historically, the MMF, the SPCAM back in the 2000s, I guess, one of the things that people got really excited about was that it did a really good job with the MJO. And the original developer of that, he wasn't even really trying for that. It just kind of happened. And in our model, we still get a reasonable MJO. It's not amazing though. And that's what this plot is kind of showing. So in the top, I have 3 Wheeler-Collattis diagrams for different variables for E3SM v2 and then the MMF down below. And you can see that the MJO peak here is weaker in all cases. The Kelvin waves are a little better, which is nice. One of the reasons that the MJO is weaker is that there were 2 features we added in recent years that made the model more realistic, but unfortunately they provided the amping effect on the MJO. So our MJO used to be better. And then so these are the top there, I've got normalized spectrum. And the bottom, I have the difference of the raw power. And this tells kind of a different story because if you look at the OLR in particular, you actually have more variance. So this is MMF minus V2. You have more variability in the field. So it's like the raw power in the MJO band is actually higher, but it doesn't stand up against the background. So yeah, so the story there is a bit more complicated than just saying the MJO is not as good, because in some ways, if you look at some, which I don't have here, but if you look at composite diagrams, the MJO propagation is better. The coherence between the wind and the precipitation is better. But in these kind of bulk spectral measures, the MJO looks worse. So I think this is the first time that anyone's been able to look at ENSO in an MMF, which is pretty exciting. And if you look here, and these maps here in the middle show the SST variance. And one of the problems in V2 is that the ENSO signal is a bit overactive. And in the MMF, it's reduced, which I initially made this plot and I got excited. But then when you start digging into the time series, you notice that the ENSO is kind of anemic. The period's not right. But it does get one, which is exciting. And this, the spectrum down below, the wavelet spectrum, shows you how the peak, you get these two bumps in the blue line there, showing that you don't really get the right period at all. After I did these historical runs, I really wanted to get at climate sensitivity and cloud feedbacks. So, and again, I couldn't do this. The typical way you do this is you run up a pre-industrial condition for a really long time, so you have a very stable baseline. I couldn't afford to do that. So I took my 1950 spin-up and I broke it into I branched off into 3 simulations. One, they're basically pre-industrial conditions with varying levels of CO2. So you have the blue line there is 1x, and then the green is 2x, and the red is 4x. And so I had to, instead of a spin up, I kind of had this spin down. And then I ran all of these for 120 years. And you get kind of the expected warming. In this difference here in the bottom, you can see you get polar amplification, land is warmer than ocean, all of the stuff that you expect to see in a global warming type scenario. And there's various other things I'm not going to show here, like intensified convection, the MJO gets stronger, stuff like that. But when I go to calculate climate sensitivity, I get a pretty high value of effective climate sensitivity, 5.2. And I also get kind of a spread depending on how I combine these runs. So I think there's actually a problem maybe in my experiment design that is giving me a value I can't quite trust. But this is still kind of in the range that you get in CBET models. It's definitely on the tail end. So looking forward, if you guys are familiar with the SAM model, that's the one we used in our CRM. And we kind of rewrote it in C++ to really leverage GPUs and made some changes. So it's different than the SAM model you might use in standalone. But we also decided that we wanted a better CRM that was more portable across architectures. So we built PAM, which is the portable atmospheric model. And we built a completely new die core. And we didn't want to write our own physics, so we stole what Scream had done because they did all the work of porting to the GPUs for us. And we also have options to run fully compressible. And we've been trying to make it much more flexible for testing and development, more modular, things like that. So, so it has a lot of potential, but it also has a lot of problems. Well, I'm not gonna say problems. It also has a lot of drawbacks, maybe issues to be addressed. And one of them is that the performance is slow, but it's actually very comparable to what you get from Scream. If you were to kind of compare the amount of physics workload on a node, you get about the same throughput. But the fact is that we can run globally at a much lower workload. We can spread that work out a little bit thinner, so we can run faster than Scream. And also, since you have 2-moment microphysics, it opens up this avenue for aerosol cloud interactions, which is a good thing. But we definitely need to tune it. And you can see in this plot here, the rainfall is much higher than the original MMF, which is already a bit higher than observation. So there's some serious biases there that we need to deal with eventually. But Scream is not really tuned yet either. So I'm also hoping that once they tune their physics, I can just steal those results, and this will just naturally get better. So in summary, the MMF is a viable climate model that you can run if you want. And if you're familiar with SPCAM, you'll get a lot of the same behaviors. There's various enhancements that you won't find in SPCAM, like we can do convective momentum transport with a 2D CRM. And we also have this weird thing called that we call CRM variance transport, where the variability within one CRM can be advected to another one, kind of through the GCM and back down. Yeah, so I guess that's all I have. I can take questions if you guys have any.
Very nice talk. Couple of questions. So why do two-dimensional CRMs instead of column or three-dimensional smaller?
Yeah, no, we do three-dimensional CRMs too. The throughput for simulations like this will be lower. You get a lot of advantages. There's been some papers like easterly waves become much more realistic with the 2D CRM. There's something about how the clouds amplify the circulation that the waves become too strong. So that gets better. Certain biases are reduced when you use 3D, but you know, it's like, depending on what you're going for, it's just not worth it because 2D gets you 95% of the way there, you know? Yeah, so like the Coriolis idea I mentioned, you know, that's one where I've tested turning on Coriolis within the CRM, and it just makes more sense to do it with 3D. But as long as your CRMs are oriented east-west, then you could also do it in 2D, and nothing says you can't.
Well, thank you. The follow-up is you're doing this globally. Why not just do it in the places where for climate sensitivity, the biggest source of uncertainty are the stratocumulus decks.
Yeah.
And the Southern Ocean to some degree. So why not just run SPCam there?
Okay, it's not SPCam.
Oh, sorry, not, sorry.
Yeah, no, it's a great question. And people have experimented with this. So a few things to note is that if you've ever seen a model that tries to switch between explicit and parameterized convection, a very weird thing happens. Like I saw this one, I forget the name of this model. This guy at Florida, at Miami, I think did it. Robert, somebody, anyway, yeah. So imagine you have a refined patch where you're going to do explicit convection and you want to have parameterized convection. The parameterized convection will react faster than the explicit convection, and it will drive subsidence into the refined zone. So you'll just get this dry hole where you were expecting clouds to form. And I think the MMF would have the same problem, that you would have this weird interaction between the areas with explicit convection and the areas with parameterized convection. So yeah, I think you would end up with a lot of unintentional consequences. The other problem, you might think, well, what if you just make the CRM more expensive, like put 3D where you want clouds to show up and 2D where, and people have done that and it works very well. The problem is it takes a lot of software engineering to make it work. Not only in the load balancing, but the only way to make it work well in the GPU is that you have to solve all CRMs in parallel all the time. So like you have an ensemble of CRMs that gets thrown across the GPU, and that only works if all the CRMs have the same dimensionality. So if you want to switch that, you basically have to have a second CRM that is load balanced differently than the first CRM, and it becomes this software engineering nightmare. So that's why we don't do it.
Thank you.
No.
You showed a precipitation figure towards the end, and the ITCC looked really, really good in both versions, or better than most models. Is that something is that common amongst cloud resolving models, and or have y'all looked into this into detail?
Well, actually, when you run coupled here, so you can see that the double ITCZ tends to be worse, and it gets much worse when you go coupled. So it looks a little better when you're using prescribed SST. And maybe this isn't the best example. When you're running with prescribed SST, there's usually this bias over here where you have too strong precip on the eastern side of the Pacific, and that tends to be much stronger in MMF models. So I'm not sure you can say it's generally better, but maybe my eyes are just always drawn to the problems.
Yeah, I think I was looking at the other figure you showed at the end, and it looked better in that color map, but yeah, the double ITCC is pretty obvious in the other figure you showed.
Yeah, I mean, I guess it's generally pretty good. Yeah.
Thank you.
Yeah.
It's-
Yeah, so do you also adapt the SAM microphysics scheme, or was this all using P3? What is the?
Yeah, so everything I showed, like for the coupled runs, is SAM one moment microphysics. Yeah, but PAM is the one that this one on the bottom here is the one that's using P3 and shock.
Ah, got it. So PAM is not the same as SAM.
Right, yeah, so they're totally different models. SAM is everything that Murat Kardinov did. We just rewrote it. And then PAM is a new die-core. Everything's based on densities. We don't do, this diagnostic partitioning of hydrometeors. The physics are different. The schemes, the coupling between processes, everything is different from the bottom up. Yeah.
No more question? So thank you again. The new Wormhole scientists come all out to host the sessions. And the next talk, on Monday, day one, day beta, the project lead introduced, we have this historical award-winning screen model. And Dr. Peter Caldwell is the chief architect of this model. So we're going to welcome Peter to give us a lecture.
Okay, thanks. And so at 45 minutes, right? For 45.
Okay.
Sounds good. All right. Yeah, so I think you guys have been hearing a lot about kind of the current status of the E3SM model. And I'm going to tell you about what we see as being the future, what we kind of have now as the future for the atmosphere modeling in E3SM. And so just to kind of orient us, what have we already done? What we've done is we've created an entirely new atmosphere model in C++ instead of Fortran that runs fast on GPU machines. And in particular, we are not, it's not a full climate model yet in the sense that it is missing the parameterizations that you need for running it kind of a conventional like NE30 grid that you probably all know about now, 100 kilometers. And so we just focus on being able to run at 3 kilometers right now. And so there's a little bit of weird nomenclature where we call the actual code that runs more or less at any resolution, might not be scientifically valid at lower resolutions, but you can run it. We call that EMXX, right? So the E3SM atmosphere model in C++ with the pluses turned 45 degrees. And so we've got EMXX as our code. And then when we do simulations, the science simulations that we're doing now, we call them SCREAM simulations for the simple cloud resolving E3SM atmosphere model. Because when we started this project, I thought that all I was doing was creating a kilometer scale global model. And so we had a different name at the time. And so we like the name SCREAM, or most of us do. Dave hates it. But yeah, so we've got those two different names. And so the things that we still have to do before this will be the official release and the only version of the atmosphere is that we need to create the scientifically credible 100-kilometer simulation. And so if you think back to the lessons you've had over the last couple of days, you probably realize that means that in particular, we need a deep convection scheme, right? So we just don't have one coded up at all yet. We also need a gravity wave direct scheme, and we need an energy fixer. And so those three pieces are just not coded up. And so we can't run at these lower resolutions in a scientifically credible way. We can run, it's stable, it just looks really weird. And then there's, like whenever you create a new model, if you think about it, that's just the beginning of the journey, right? Like we've been trying to improve the E3SM atmosphere model ever since we branched from CESM, and they've been trying to improve it for like 30 years before that. And so there's a lot of work to do still, right? So the model runs, but there's a lot more evaluation that we need to do. And there's also a lot that we can do to make the model even more computationally efficient. So we're still working hard on that. But let's step back for a minute and ask the question of why did we do this? It's kind of annoying to have to switch languages from Fortran to C++. And so the reason why is really the second E in E3SM, so exascale. And so at least in the US, what exascale means is using GPUs, right? And so GPUs provide another form of parallelism beyond just the inter-node parallelism that we get from MPI. And they're relatively new, and the programming strategies you have to use on them are different. And so, yeah, so we basically need to rewrite the code a lot in order to get them to work. Now, you can extend a Fortran code and create a GPU working version of the model, but a problem is that, well, so one problem is that the old atmosphere model, any atmosphere model, it's like millions of lines of code, and trying to port all of that code, extend all of that code to work with GPUs is a very cumbersome and unpleasant exercise that we tried to do, and just no one had the appetite for it. So it's actually easier for us to get excited about writing a new model that had all new code, and we were able to use modern software engineering and things like that in order to make this transition. Another big issue with GPUs is that there are currently 3 different vendors of GPUs, so NVIDIA, AMD, and Intel, and each of them has come up with a different, let's call it a programming language or extension that you need to use in order to run on their machines. And so we could code the model so that it works just on NVIDIA using CUDA, but then we wouldn't be able to use DOE's exascale machines that are AMD, so the Frontier machine that exists now, or the upcoming, well, I guess Aurora exists now as well, and that's Intel. And so in addition, and I think this is really the main reason to switch to C++ is that C++ is a famously very abstract language. You can do whatever you want in it, and that causes headaches, but it also makes it really easy to make the model so flexible that you can get it to run using these different extensions for the 3 different kinds of GPUs, right? It's more or less the only way that you can write a code that works across all the different flavors of GPUs that we have right now. It also works on CPUs. Basically, you can run on any of these different machines if you use C++, as long as you use what's called a performance portability package. And so in our case, we're using something called Cocos, which was developed by Sandia. There's also, you might have heard of Raja. It's basically the same thing developed by Lawrence Livermore. And there's other packages like that as well. And so C++ plus an existing performance portability package equals ability to run on more or less any kind of architecture that's out there. And so, yeah, that's what we did. And so, as I mentioned before, there was a lot of excitement about this that got over the hump of, oh my God, we have to rewrite our code just to run on a different machine. It's going to give us the same answers. Why should we do this? And so one thing we're really excited about is the ability to have a clean sheet model. So have a model that's just completely distinct from the CESM model, which I personally, if you think about the CMIP archive and all the different modeling centers worldwide, we have this issue where a lot of the models are kind of copies of each other, and so they're not independent. And that really confuses us when we go to do multi-model analysis, because we think like, oh, I have 50 independent samples, and I really don't. I maybe have like 15 or 20. And so we've created another independent sample in this way. We're also able to bring in modern software engineering, which I think we've been really excited about. It means that we can reuse a lot more code. And so we have less code to learn and less code to write. That's great. It also allows us to do some things that I think you'll be really excited about in terms of how we write our output and what kind of output you can write, which I'll talk about later. And so all in all, I think it was pretty successful. And so that's kind of on the computer science side why we wanted to do this. But then on the climate science side, our ultimate goal is to do simulations that are somehow better and that give us a better sense of what future climate is going to be like. And so the thing that we can do by switching to code that runs really fast on GPUs is that it's a perfect fit for doing very high resolution simulations. And the reason for this is that GPUs don't actually do any single calculation faster at all. They can just do more calculations in parallel, right? So it's an additional dimension of parallelism. And so if you think about, okay, well, how do I get that parallelism? It turns out that at conventional resolutions, we're already using all of the available parallelism. We're essentially running with as many nodes as we possibly can most of the time. So you're just not going to get any faster by using GPUs on 100-kilometer simulations. So that's kind of a bummer. And it actually took me longer than it would hope to figure out that we actually need to move to higher resolution in order to make use of these GPUs. And we also, I think we are lucky to have the GPUs because higher resolution is really important for getting better answers, in my opinion, right? So we can do much finer simulations, much higher resolution simulations for, it's still a little bit more expensive. It's still substantially more expensive because you have to use a smaller time step, but you can parallelize over all your columns. So, so that's one piece. And so my feeling about the benefits of very high resolution, we're talking like kilometer scale globally here, is that one, I think that there's a lot of processes in the atmosphere and interactions between processes that we're just not resolving and not even thinking about in terms of the parameterizations we use, and we just naturally get when we are resolving things. So deep convection being kind of the obvious example. And, so from that perspective, I think that we're going to just get more accurate predictions of kind of large scale things like climate sensitivity out of this sort of a model. So that's one thing. And then more or less independently of that, there's another real issue, I think, which is that I feel like in 2024, our job as climate scientists is to largely help with adaptation, right? And adaptation is local. It's like, do I build this bridge higher? What do I do with this dam? Things like that. And so we need just very high resolution output in order to do that. And so downscaling is one option, but there are often ambiguities about whether you're getting the right answer when you're doing some sort of a downscaling of coarse resolution climate simulations. And so if you can just simulate at 3 kilometers directly, that's probably going to give you about the best answer you can get. And so that is what we're doing. And so in particular, things that we've found, that it's just, it's so blindingly obvious that if you resolve a mountain, you're going to get better snowpack. You're going to get better precipitation, right? And so there's not anything like mind-blowingly sophisticated here for a lot of the benefits we get. It's just that we couldn't not get the benefit from actually capturing the processes that we have. So. Okay, and so that's kind of background for why we did what we did. And so let me talk a little bit about what we actually did. And so to start off, so the fluid dynamics that we use, it's actually a non-hydrostatic extension of the spectral element dicore that E3SM has used since its inception. And that's kind of a theme, is that we're extending what E3SM has done to work at high resolution for a lot of these processes. So so non-hydrostatic spectral element dicore. For the radiation, we're using the same RTMG, but the newer version has a P on the end, which is for parallel, because it's supposed to run on GPUs. We ended up rewriting the RTMGP package in C++ because the GPU extensions that existed were too slow for us. So that's our radiation. P3 microphysics, which is the same as the newest version of the EAM, except our version is, has diverged a little bit from the version that's in V3. Our aerosol is currently the aerosol effects are prescribed, so we don't actually have aerosol in the model, we just have the impact on microphysics, the impact on radiation included as basically files that we read in. There is a whole separate project that is porting the MAM modal aerosol model that you probably heard about from the rest of EAM. We're porting that to C++ Cocos as well. And so I think that's hopefully next 6 months-ish, we should have that. And then the turbulence cloud formation is simple higher order closure or shock, which you can think of as a simplified version of CLUB. It's very similar in terms of kind of the PDF sort of cloud scheme as well, and the coupling between a higher order turbulent closure and PDF cloud scheme. And I have no idea why we just switched slides. So parameterized deep convection, we just don't have, as I mentioned a couple times before. We also use the PG2 grid, so the finite volume 2x2s in each of our spectral elements that you've probably heard of before from EAM as well. Okay, and so one of the things I'm most excited about is the change in software design that we've been able to include. And so from the get-go, we had a couple of goals, having worked on the old EAM for a long time and been irritated by it. And so one of the things that we did is we really, from the get-go, we wanted to be able to break each function and the whole model up and run it separately from the rest of the code. And if you've tried to do that in the old EAM, you will start pulling out different modules, and then you'll have more modules, and eventually you'll have the whole code again. And so we have really tried to separate out the actual physics calls into code that doesn't have a lot of dependencies. And that allows us to have unit tests, which are great. I'll talk more about later. And so one piece of that is that within each process, we have the process representation is kind of isolated, and it only communicates with the kind of higher level pieces of the code via an interface layer. So each process has an interface and the actual code representation. Some of EAM has this as well, but we're more rigid on it. Each of those processes is an abstract class within C++, or we have an abstract class, and each process is an example of that class. And that allows us to have a lot of helper functions that you can use in all of the different processes. It also allows us to have each of these processes, just kind of be considered identically by the code. And so you can swap the order of each of the processes. You can just chuck one out, you can add a new one. You know what your interface needs to be. Makes it a lot easier to design code and to swap things out. And so you can actually do that on the fly. You can say, I want to substep these three processes together. I want to not include this process. I want to do whatever you want. And so I think that's going to be really helpful for understanding the numerics of the code and making sure it works right for the right reasons. So that's, I think, an important piece. And so we have this idea of these abstract processes, and we have to talk about how you pass variables between the different processes. And that is entirely managed by what we call the field manager, which is a lot like pbuff that you might have heard of before, but it is, instead of having some things via pbuff, some things actually via the function signature, and some things just loaded in other ways. You pass everything through the field manager, basically. And so that makes it a lot easier to know that you're getting everything when you call a process. And then on top of that, we have the atmosphere driver that tells you which order for your processes and things like that. And so this is the slide about our atmosphere driver, which is in the center of that graphic there. And so we already talked about the physical processes that are all coupled together via the driver. But the driver also handles a bunch of other stuff. So in particular, it handles all of the different runtime options. So it loads in all of the options that you set via your run script. It handles what you do with your input and output, including what you want for your input and output, what the frequency is, things like that. And it also talks to the coupler and the surface models. And in particular, one thing that is different between us and the old EAM is that we decided that we want the atmosphere to not just be we don't want to split the atmosphere into a couple of different calls, like there's the TFIS AC, TFIS BC calls you might remember from EAM. And so instead, we have one atmosphere call and it just runs through all of the atmosphere processes. And then we insist that the surface model is called after all of the atmosphere processes, or equivalently before, since we're running around in a circle. And so that makes our coding a lot easier. In terms of setting the input options, I think I'm going to skip down to the lower bullet because that's really the relevant one. So I guess first I should say that EMXX is it is an E3SM model, and so it works and seen the same way as every other time you want to run E3SM. You are going to use what is it? The XML change, XML query for all the kind of scene-based commands. Your run scripts are going to look pretty much identical. But the one difference is that when you want to change atmosphere options, you're going to use ATM change and ATM query. And so that mimics the behavior that SEAM options use. And so you should be familiar, hopefully, with that kind of similar as before. We don't have name lists instead. So we want you to use ATM change, ATM query for everything instead. And instead of name lists, behind the scenes, the thing you shouldn't change, but maybe you should know about, is that we are using YAML files, which is the more kind of modern version of name lists that's more specific for C++. And so YAML files have a lot more structure, and that allows, and so we have an example on the right-hand side, and that allows you to be more clear about what you're trying to specify. It's more hierarchical, so you can have a different section for each of your different processes. And so hopefully that's a positive change. Okay. And in terms of writing output, this is the thing I think people will be most excited about. There were some limitations in the old model, like you could only have like 9 output streams, which makes life hard sometimes. And so in our new model, you can have as many output streams as you want. You can change the names of them if you want. We mostly just call them like H1 through H100, whatever we want. You can also, very excitingly, you can write your output just directly onto whatever grid you want. This is really important for us when we're running at 3 kilometers globally. It's like massive, like terabytes and terabytes anytime you want to write 3D output. And so a lot of times we just write them out at any 30, right? And so that's been, I think, a game changer for us. We can also just write things directly onto pressure levels, or I think we've at least been trying to be able to write them just onto like the actual geopotential levels as well. And so there's a lot of flexibility in terms of the output. One thing that's a little bit, I think, just a negative of EMXX right now is the way that we decided what output you can write, in the sense that the old EAM allowed you to just, put an output call wherever in the code you want, which caused a lot of dependencies in terms of trying to isolate things and have our unit tests. And so instead, we just decided to make our lives easier that you can only currently write outputs that are in your field manager. And so basically you have things in your field manager if you are trying to pass them between processes. So anything in there you can write out anytime, but you have to add things to your field manager if you want to expose them to writing output, because we want output to be a process as well. So that makes life a little bit harder. We've also added the capability to be able to write out any function of variables in the field manager that you want. And so that extends the capability a lot. We also have a really cool functionality where you can just in one line ask to write the time tendency, the tendency due to any process, whatever frequency you want. And so that's super helpful if you're trying to do budgets. So that's useful. We have COSP satellite simulator output currently just for ITSCIP, but that's just because we haven't wired it all up yet. So yeah, that's that. In terms of testing, so we inherit all the tests that that E3SM has. So all the EAM tests we can do as well. But in addition to that, we have these magic unit tests I talked about before. We have hundreds of them. We have an example on our C dashboard of a lot of passing tests. And I really think that unit tests, I mean, like in software engineering, this is what everybody does because it's the right thing to do. And the reason why it's the right thing to do is because instead of saying E3SM crashed and it gives me this error message, now I have to look through all of the code to try to figure out why. We usually are catching all of our errors in a particular function. This function crashed. And so that's just a ton less code to look through. And so we spend a lot more of our time debugging these unit tests, but as a result, I think we're a lot more efficient in finding our problems. And I've been shocked at how frequently we'll code something up new, we'll run it, and it won't crash. Like, when does that happen? Like, never. So it's been pretty amazing. I think it's been really good for us. Having all these unit tests has also allowed us to have continuous integration, which is the idea that whenever we want to merge a pull request, instead of having a bunch of experts have to look at things, we just have a bunch of tests automatically run. If it passes all the tests, then we integrate it most of the time. If it's a bit for bit change that we've made, we actually don't ever look at it. It just is integrated automatically. And so that, I think, has really allowed us to speed up as well. E3SM as a whole tends to, in any particular component, only integrate maybe one change a day, and we integrate maybe 5 changes a day because of our continuous integration. So yeah, and we also have nightly tests because sometimes our unit tests don't catch everything. In terms of computational performance, Wuyin mentioned that we won an award, and that was for getting 1.25 simulated years per day at 3 kilometers globally, which is kind of mind-blowing, I think, right? Like, a quarter degree model runs like 5 simulated years per day or something. So that is amazing, but we had to use all of the world's fastest supercomputer in order to get that kind of a speed. So realistically, we're not doing that. We actually run with, instead of, I think, on Frontier, there's on the order of 8,000 nodes. We run on about 2,000 nodes most of the time for our Frontier jobs. And so look at how much more cheap it is for that. So this is if we're using all of Frontier, we use about 160,000 node hours per simulated year, but we only use 90,000 node hours per simulated year if we use 2,048 nodes. And if we go down to 512 nodes, which is starting to approach the minimum number that we can fit into memory, we use 71,000, right? And so this is something where the, on CPUs, you scale a lot better than that. You can just run on as many nodes as you can fit the problem into, and you are going to not lose that much efficiency. And it's just kind of an intrinsic thing about GPUs that they don't scale very well. And the reason is because they perform all their calculations so fast that you end up spending a lot larger fraction of your time doing the communication that is the thing that is not perfectly scalable in MPI. So that's an important thing to think about. And then another number just to throw out is that while we can't do scientifically credible simulations right now at 100-kilometer resolution, we can run in that configuration, and we can easily get over 100 simulated years per day at NE30. And so it's pretty fast. And that is on CPUs because there's no real benefit of running such a low amount of parallelization on GPUs. So, yeah.
Sorry, this might be a dumb question, but how does that compare to like E right now?
Chris or someone else? Maybe factor of,
3 times faster, maybe.
yeah, so
It's physics is very new.
yeah,
We also,
the aerosol is way expensive, yeah. So, okay, yeah, so computational performance. I have no idea how much time I've taken, so am I almost out of time?
Including Q&A 15.
I have 15, okay, perfect, I think I'm on track then. And so, one kind of weird thing about this model is that it's so expensive to run these simulations at 3 kilometers that my expectation, well, I think the thing I'm sure of is that not everyone's going to get to do these simulations, right? There's just not enough computer time in the world for this. And so it becomes a lot more important for us to be really considerate when we do simulations, make sure that they're available and that they're easy for everyone to use. And hopefully they have all of the output that people want to analyze. And so in that context, just like the rest of E3SM, we're committed to making all of our simulations available after we submit the first paper that we're writing about each of them. And so I've listed all the simulations that we're planning, the big kind of hero simulations we're planning on doing. Green are things that are already available. Orange are things that we have finished and are writing papers about or are in process right now. And red are things that are kind of, we're hoping to start soon. And so kind of the classic thing to do with these kilometer scale atmosphere models is the 40-day simulations from the Diamond inner comparison. We participated in Diamond 2. That was our first simulation. We used Fortran version of the code for that. And so basically all of our data is available on NERSC if you have access to it. And you can also get this other one from the actual Diamond 2 inner comparison. We then ran a set of 4 40-day simulations. Once that was the first thing we did once we got the C++ code up and running. And that's also available on NERSC, including through NERSC Globus and Science Gateways as well. And one kind of humorous anecdote about this is, so we first did this 40-day Fortran simulation. It took us about a month to finish, and we were so happy. It was like this huge accomplishment. And then we wrote the C++ code and submitted our first 40-day job. And I came back after the weekend and was like, well, what's the status? I was like, oh, I think it finished. So just so much faster, you know, both because we're running on much bigger machines, because the GPUs help, because the C++ helps. And so, yeah, it's really been kind of amazing for us. So we have finished what's called the Sess-Potter experiment. So a pair of 13-month simulations, one's current climate, which is interesting in itself to analyze our climatology. And then one is just uniform plus 4K SST increase. This allows us to get at climate sensitivity. So writing a paper about that now, it'll be out soon. We're also working on a decadal current climate simulation right now. It's 20 years long. We think it's probably going to take us a whole wall year to finish. We're going to do a future kind of AMIP future kind of a simulation as well. Eventually, it's probably going to be next year. We're going to start a pair of 13-month AMIP or 13-month another current climate simulation, and then pre-industrial aerosol simulation to get at cloud aerosol effects. That'll be done. We'll start that hopefully this month. And then probably a year out from now, we're going to start working on coupled kilometer scale simulations as well. Okay, and so one way that we can get around the fact that these models are insanely expensive is just to provide the data. And so you don't actually run the model, you just analyze the data. But there are other things that we can do that I think we're super well. And so one of those is that we have a doubly periodic configuration. So this is like the kilometer scale analog of the single column model that you've probably heard of already. I think that there's a much better consistency between what you see in the global model and what you see in the doubly periodic version, because the single column model tends to kind of snap to certain model levels, and it can get kind of pathological, but we actually have we have a whole grid for the doubly periodic mode. So can run that, uses the same set of 30 or so case studies that are available now. So super easy to run. We also have the regionally refined version of the model, which is just the same thing as EM has always had. And so we can do simulations there with that, down to 800 meters is what we've done so far. To talk just a little bit about the things that the model does well, things the model doesn't do well. We're climate scientists after all. Kind of maybe the obvious things, if you're resolving storms, you do a good job with storms. Same thing with orographic effects. The PDFs of precipitation intensity, so this problem of models drizzling too much, not getting the extreme events, is much, much better in our model. And the only thing on this page that I think is really a surprise is that we also do really pretty well in terms of like stratocumulus, boundary layer clouds. And I think that this is because we have this shock, so club-like parameterization for shallow convection and stratocumulus, which is much more sophisticated than models of this caliber usually use. So that's something I think is a unique advantage of us. There's a lot left to fix, and I have 3 examples here that I think are basically different aspects of the same problem. And so one problem that I think is kind of ubiquitous about global kilometer scale models is atmosphere models, is that they tend to create what we call popcorn convection, which we see in that upper plot, which is, it kind of looks like the simulation has measles. It has a lot of really intense cores that are quite small. It's not doing as great a job of aggregating. We can get these popcorn to actually aggregate themselves, but they're still kind of, too much isolated convection. And related to that, we tend to have a situation where you have like shallow convection, it's shallow, 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 and then all of a sudden it pops up to the tropopause, right? And so we're not getting clouds at the mid-levels, and associated with that, we have dry bias in water vapor kind of in the mid-troposphere. So another issue that we've been struggling with is that our land surface temperatures are a little bit too warm as well. Okay, so I think this is my last slide. So improve performance, improve climate, and complete the low resolution parameterizations is kind of the big picture of what we're trying to do next. So, and I think that's it. Yep. So questions? Yeah.
Nice talk. I'm so excited to hear the effort to make those processes independent, because it can be a huge headache sometimes when we add new processes to and debug the model. My question is, are those unit test tools available for the users, and whether they are usable for the current version of E3SM, or it just specific for the new version?
Yeah. So the easy answer is that no, the easy answer is that these unit tests are specific to EMXX. And we had to redesign the model basically in order to make them work with EMXX. So that's that piece. In terms of whether the unit tests are available to everyone, if you're using EMXX, we expect you to create unit tests. And we have a framework for how to do that. I don't think we have good documentation on that yet, but we're working on it. And so, yeah, we have tools, but you have to write the unit tests yourself, right? Because they're often like, don't allow water to be negative and, things like that. So specific to each process. Yeah.
So in
the strong scaling figure you showed,
Mhm.
that one of the test case you did is using, I see that you use like up to 8,000 nodes. I'm wondering what kind of configuration or experiment are we gonna do with that many like, numbers of nodes cores? Because in my experience, I've never used that many cores on a climate model.
Yeah, so I think basically the higher resolution you go, the easier it is to use more cores, right? And so for like 100-kilometer resolution, yeah, you can't get anywhere near this. For the 3-kilometer simulate global 3-kilometer, dividing the world into 3-kilometer tiles, it's pretty easy for us to use that many. As I kind of showed before, it's not all that computationally efficient, and that we're using almost twice as many node hours per simulated year as if we used a quarter of that size. So yeah, we're not quite in the sweet spot for using 8,000 nodes, but we can. But if we want to use a 1-kilometer model, we'd probably be strong scaling still at 8,000 nodes.
Yeah. Do you have any sort of documentation for those of us who are used to Fortran but want to transition to C++?
That's a great question. Yeah, so I think the answer, so what we're doing right now, when I left on travel 10 days ago, we were working on our user guide, which is just basically how to run the model. The next step that we want to do is the developer's guide. And so that is going to be exactly what you want. Yeah, and one kind of additional comment I'll make there is that when we started this process, I hadn't used C++, and I got myself a C++ book and I started reading it, and I quickly realized that, C++ is like, I don't know, to call it a language is almost too narrow, right? It's like this broad thing. We only use like a very small fraction of the options in C++, and we have our own style, and then we have Cocos on top of it. And so I think really the way to start coding in it is probably going to be to read our non-existent developer guide. Yeah, so, but hopefully in like maybe 3 months' time, we'll have that done. Great. Yeah. Yeah.
So all the examples you showed us are global simulations, is that correct?
Yeah, I think all the examples I showed, yeah, and so that's been kind of our core, that's what we've been focusing on, is doing these global simulations. But we have also done regional and refined simulations. They seem to work pretty well. We use a lot of doubly-periodic simulations for, yeah, I guess if I was going to develop a new parameterization, probably start with doubly-periodic, make sure it works, and then do some regional or refined simulations, make sure those work before we actually go to these global simulations. Yeah.
Towards your regionally refined stuff, so I actually do simulations of wind farms, like late resolve stuff, but
yeah,
we need to do unsteady, atmospheric phenomenon to bring that in. Can you speak to how far you can push your resolution down to basically set up my flows, right? Which go down to my.
Yeah. So what I'll say is that we have run pretty successfully at 800 meters. We have not validated that we work as a large eddy simulation yet, which I think is probably what you want. One thing that we don't have in the model right now is horizontal turbulence. Turbulence is just in the vertical direction, which is kind of something that you need in order to be a credible LES. And so it's on our list of things to do. To push towards the higher resolution and also to have the horizontal turbulence. So yeah, not quite yet.
So this morning we heard many exciting development and application for the existing model and the future models. And all this, and then together with the past 2 days, mostly about the couple physical systems. But next, we are going to hear more. Also have exciting development beyond this couple physical system. And the next one, we're going to hear from And then, Jennifer going to present it? Okay. From Jennifer also, it's here at Berkeley Lab. About HES.
Hi again, everybody. Again, Jennifer Holm. I'm just doing a very, very quick 2 slides introduction of what is the Human Systems Feedback Group. So yeah, as we have all these different component developments, E3SM, as you guys heard about in the very, very first day, we also have these main science drivers. So as we're, developing our code and our models, we also need to be testing very, very big science questions. And we have these really big science driver campaign groups. So I'm one of the co-leads of the section are in the red boxes. So the HES group is what's called the Human Earth Systems Feedback Group. So yeah, in E3SM, we kind of have these huge, big 3 science drivers where, of course, we care about understanding water cycle changes on a global scale. And then we care about the human feedbacks and care about, really I'm trying to understand more things with polar processes and sea level rise. So just a quick introduction of why the human Earth system feedback is so important is because, with climate change, we are obviously changing our planet. We're out here logging the land, changing different managed systems, doing different things with crops, different things with the forest system, different things with aerosols into the atmosphere with our pollutants. And so all of that we're trying to capture as well in our Earth system model. And I feel like E3SM, we're one of the really cutting edge major climate change models. It's really representing humans for the very first time. It's very challenging, but we are really trying to look at this coupled human system. And that's what Alan Vittorio is going to talk about next. Just one more quick slide about the HES group. This is where also a lot of the biogeochemistry is really done. So a lot of our global coupled biogeochemistry simulations. And something that we plan to hopefully start doing, we haven't started yet, but we really want to look at decarbonization scenarios. So as the whole just human Earth sector going forward, we're all trying to decarbonize, our different energy sector areas, our global carbon footprint. What is that going to mean in a climate model? That's never really been done. So we've coupled in this GCAM system that you're going to hear about next that's able for the first time to look at what it means to even just decarbonize different energy sectors. And yeah, so those are kind of the 3 main kind of things that we work on. Everything that you see in bold, we're doing prognostic CO2 throughout the whole Earth system, really looking at areas of biogeochemistry and the ocean and the land, modeling, land management, crops, land use change. And all those things will go into these global decarbonization scenarios that we hope to start in the next year or 2, which we're very excited about. Okay, so that's just a very quick primer what our science campaign is. And now I'll pass it over to Alan Vittorio.
Thanks, Jennifer. Yeah, I'm Alan Vittorio. I'm at Berkeley Lab here. But my team that works on this GCAM E3SM coupling, the rest of them are largely from Pacific Northwest Lab, including Eva Sinha, Tim Shippert, who has since moved on, actually retired, but is foundational in all this work, Dolly Howe, Baldwin Singh, and Ben Von Lamberty. And I also need to mention Kate Calvin, who isn't listed here, but whose work is also very fundamental to actually getting this working. So it's a little bit of an interlude here. I'm going to talk about humans and the miscellaneous physical processes, but for aware, one of the reasons why we do a lot of this work is to understand how humans are changing the environment and if there are ways that we can mitigate or adapt to that. So I'm briefly going to talk about scenario-based modeling. I think many of you may be familiar with it, the basic IPCC or Intergovernmental Panel on Climate Change process. And then I'm mostly going to focus on what is E3SM GCAM, what are we doing, what have we done, and then there's some preliminary results that I will share with you. So in the context of IPCC, scenario-based modeling looks like this. It's a one-way process. There are human system modeling groups that develop scenarios. And those scenarios basically include land projection, so land use, land cover change, and emissions and concentrations of various atmospheric constituents. And then that information is usually protected for 100 years or more. Some there are 300-year simulations, but they're given to the Earth system groups to do their climate and Earth system simulations and see how things change. And then the outputs of that are then passed on to additional modeling groups that look at impacts in various sectors and relate those impacts back to the scenarios. Well, is this really how things work in the world? What we're seeing is that people actually respond to the changes in the environment, right? So you have impacts on agriculture, you have impacts on water availability, you have different types of extreme events, and the human systems are actually responding in real time. You may be familiar with a lot of the different adaptation and mitigation strategies that have been proposed through over the years. And so the systems are responding, and then that changes the projections, that changes our emissions and land use as the Earth system is changing. And so we want to capture that in our modeling system. That's why we're adding humans into this model. So what we have done is we've created another component that's on the same level as the other components, and it's the human component, and it uses the shared coupling infrastructure. And there's a large advantage to this because we've done a previous version where we were directly coupled to the land. It was a pilot project to see what kind of effects happen when you include feedbacks. But now here we can actually advance the model. There's more efficient updating of the code. We can update the other components. We can update our components. We can update our primary human model, which I'll talk about. It's much easier to add new feedback to the system. The coupling infrastructure is there, and we just can use that to pass variables, not only between components that we're using, but to new components. We're actually exploring some of the coupling with the river module, for example, from our human system. And then it facilitates a new scenario where we're no longer beholden to existing scenarios that have been developed through the IPCC process or the integrated assessment modeling consortium process. We can actually run GChem, create our own scenarios, and run them in E3SM. Our current status is that we're running with the 2.1 version of E3SM and GChem 6. And the feedbacks that we're passing, and I'll talk a little more about what these are 5-year terrestrial productivity feedbacks from the Earth system model back into the human model. And we're right now in the process of testing our final coupling pieces, is actually getting the CO2 emissions from the human model also every 5 years into the atmosphere model. So there's a little more detail on what this looks like. The E3SM human component is made up of the global change analysis model, which is an IPCC class model that creates scenarios. It has these components: land, water, energy, economy, and is driven by different policy considerations. And it generates the CO2 emissions and land use and land cover and the other atmospheric constituents that drive EAM. Right, and so you may be familiar with some of that. These arrows going from right to left are kind of the standard process of the scenario passing from the human model to the Earth system model, along with a lot of other atmospheric constituents that I'll bring up shortly. The feedbacks here are these that we've introduced with coupling this are the terrestrial productivity feedbacks that you see coming back from E3SM. And it's not just GChem that's needed to do this. The other part of the human component is there's a lot of coupling infrastructure in that human box that is needed. And if you're curious about that detail, I can talk about it. But there's a lot going on there. There's a whole workflow that we had to develop for this to happen because we first need a scenario. We need to develop a scenario, and we can think of the existing scenarios, the SSP-RCP scenarios that you may be familiar with, the shared socioeconomic pathways and the representative concentration pathways. But we're more interested, like Jennifer mentioned, in some of these decarbonization scenarios. So net zero type scenarios, the nationally determined contribution scenarios that were put forth in the Paris Agreement. And we can use those, we can build new ones. The GChem team has done lots of different scenarios. We can draw from their expertise and what they've done. And there are different choices we can make about the land carbon value. And that's listed here for a reason I'll show later. But once we develop the scenario that we want to run, we actually have to configure GChem and run it. We need a standalone run of GChem for a couple of reasons. One is that we're only actively passing CO2 emissions between the two models, and there are a lot of other pieces that go to EAM. The second reason is if we're doing a representative concentration pathway run, we need the carbon price path for that. So it takes thousands of iterations of the whole 100-year time series for GChem to solve for a particular forcing. And we can't do that every 5 years with an E3SM. So that's another reason why we need that standalone GCAM. But that again allows us to create our own scenarios for this. After that, there's a whole processing of the GCAM outputs that we need, largely for the other atmospheric constituents, but also for the carbon price path. I'm going to show some more detail on that. And then once we have all that, we specify it in our E3SM GCAM system and run it. This is what the atmospheric constituents look like. I'm going to break down. There are up to 23 files needed for input for a particular scenario. 21 if we're actively coupling the CO2 emissions, and their aerosol emissions. There's ozone tracers and other GHG concentrations. And so we have the ability to shut off our CO2 emissions passing, because right now in the example I'm going to show you, it's not fully active. This whole process takes 3 steps. There's a step of processing the GCAM outputs so that it can be entered into the standard CMIP processing software for the coupled model and comparison project protocol. And then we run that software on those outputs to get the kind of the CMIP format. And then we have to process those files into the EAM format. So it takes a bit of work, but we've worked through this workflow, and we do have one scenario now that we've completed all of this for. There are a couple other key configurations that we can do with E3SM GCAM that are unique, and that's how we turn the feedbacks on and off. I mentioned we can turn the CO2 emission feed forward on and off. We can also turn the productivity feedbacks, the threshold feedbacks on and off. And we can control them separately between the crop scaling. Should explain what that means. The crop feedbacks. And so when we do our feedbacks, GCAM has a different initial state of what its carbon content is, of what its crop yields are, and those sorts of things. And so rather than passing feedbacks directly, we actually create scaling factors. And so our feedbacks are passed through in terms of, we calculate the scaling from 1 year to a baseline in E3SM, and then we pass that scaling information back to GCAM. So that's why here it's called agricultural yield scaling or potential carbon density scaling. And this carbon density is only relevant when we value carbon in the landscape. Otherwise, GCAM doesn't really care how that carbon changes. We can also change whether we want to actually calculate the feedbacks and save them to a file, or we want to read feedbacks that have been pre-calculated. And that can be useful for different types of scientific experiments that we'd like to do. I'm going to show you how we've configured our current example. This is an active atmosphere, land, and human run. It's not quite scientifically valid yet in this case. We have a GCAM configuration that we run. It starts in 2015. It's based on SSV2 RCP 4.5. And we do have land carbon value in the landscape. It's phasing 25% of the carbon price. The E3SM model is configured with the atmosphere CO2 cycle on. And so we are requiring the CO2 emissions both from the ocean and from the land, and the files that we're providing in this case are emissions files. There's about a 1 degree land and human grid. The atmosphere grid is the ND30 grid you heard about. It's about 1.5 degrees. We have a data ocean and sea ice right now. We're not that the ocean isn't active right now, and that's on a 30 to 60 kilometer grid. The land ice module and the river module are off. We do standard spin up to 1850 with this configuration, transient historical to get to our initial conditions in 2015. And then we start our run with the human component active. We've done 2 runs with this, one with the threshold feedbacks on and one with them off. And we're toggling the crop yields and the carbon density scalars together. We're not looking at them separately right now. Some of the things that make this not quite scientifically valid are that when we ran this, we didn't have all of the files for SSV2 RCP 4.5 processed and ready to go. So we're using our anthropogenic CO2 emissions are actually a 585 scenario, which doesn't quite match, but it's running. And then the ocean emissions are a 37 scenario. But we do now have the 245 set up for our current testing, and the biogeochemistry module is on in the land. So here's an example of what the feedbacks look like. And so I said these are scaling factors. So one is there's no change in the human model. What I'm showing here are the global crop scalars for all these different crops that GCAM has. They have a lot of different crops and they are unique. The interesting thing I want to point out here is that E3SM, or I should say ELM, in this configuration only has one crop and it's a generic crop. But you see we get values, unique values for each of these crops. And I will explain how we do that shortly. I first want to show what the non-crop vegetation scalars look like. And the interesting thing here is you can see there's really only forest, grassland, shrubland, and pasture in GCAM in terms of non-crop vegetation. But the land model in E3SM has 8 different biogeographical forest types, 3 grass types, 3 shrub types. And so with this data, we have to transform and map these the opposite direction, right? We're going from one crop to many, and the non-crop vegetation, we're going from many types to one forest type, for example. So I just wanted to point out how we get distinct scaling values for all of these different crops and land types. And there are 2 different ways. And the first way is really due to a geographic heterogeneity. And so this is maybe not the most intuitive way you think about getting this, but this is how we go from one ELM crop to many GCAM crops. And it's just because crops are grown in different places and different places have different feedback signals, right? And so you can see that on the left, I should use that. On the left here, these are actually aggregated to the whole US, but they're actually 23 distinct land units. But even with that aggregation to the US, you still have unique scaling values for different crops. But you can also get that even with just a couple, or even within a particular land unit. On the right is Japan, where there's only 2 land units, and you still have a few different unique crop signatures. The other way that we get this heterogeneity in our feedbacks is due to distinct plant types. Maybe the more intuitive way to think about it, the upper left is the crop, the upper right is forest, and then grassland on the bottom right, and shrubland on the lower left. These are the vegetation scalars in 2060. And what you can see is if you look at a particular place, you have a different feedback parameter for different vegetation types. And that's just because the different vegetation responds differently to the different conditions. And then just a couple of quick results slides. This is showing the change in land allocation for the scenario with the feedback simulation minus the non-feedback simulation. And the most prominent one here is this red line. That's actually a decrease in crop area over the period, but you can also see it's highly variable. And so what we're seeing here is actually the interannual, since the 5-year feedback is interperiod, but it's really drawn from the interannual variability in crop productivity, right? And so we're actually capturing this as we go along through the scenario. And so the human system's responding to that, says, oh, we've had a really bad crop output here. We're going to plant less crops next year in this area. And so it gets shifted around. This also shifts around the other land cover. And then we get impacts on the Earth system. In particular, the one global value that tends to be affected by these feedbacks is terrestrial carbon. Showing here, there's a difference. It's not huge. Other variables like global temperature are less affected by these type of feedbacks being introduced. And that's also due to the type of feedback. We're just introducing terrestrial feedbacks here. There are other feedbacks that we can now add now that we have the system running. And then this is just a regional plot. The regional differences are usually more pronounced for many variables, and that's because they're often driven by these regional land use changes. This is showing near surface temperature changes on the order of 1 degree centigrade. And on the right, the left is our simulation. On the right is a previous simulation with our old E3SM model. But basically both showing that you get this geographic differentiation and that the values are in line with what's expected from the effects of land use change on your surface temperature. In summary, I want to point out that these feedbacks do matter, but it also does depend on the scenario and on the models themselves. I didn't go too deep into that, but if you have any questions about that, I can answer them. And generally, the global effects are small with the exception of the carbon, and that's largely influenced not just by the type of vegetation that's out there, but also by ongoing land cover change is going to really affect that. The regional Earth system effects are consistent with what we expect from land cover change. And this last point, I just want to say that it's really key. These feedbacks are really key to understanding the coevolution of both human and Earth systems. or the evolution of the system as a whole. It's one system really. In red here, I note that we need robust model development, and that includes both ensuring that there's consistency between the two models, particularly human and Earth. There are a lot of things that are defined differently and treated differently in the models, and that's been a big challenge over the years. But a really important thing here is this facilitates this new scenario development that I pointed out. And so next steps is continued advancement, which we are now can do with this type of system. We've actually completed the code to couple the CO2 emissions with the Earth system model. We're testing that this week. And so we're actually moving towards our full testing of this system as designed. Finally, we're pretty excited about that. We have completed a full SSP2 RCP 4.5 configuration, so we're working with that. And we just want to move forward with new scenarios and actually doing some science with this new system. Thanks for your attention. Yes.
Thanks for the overview, Alan. Just a question of curiosity. What is a carbon price pad?
Yeah, so one of the ways that the human models drive their projection to a forcing target is that they implement a policy is basically a carbon price, right? And you can have it could be $20 now and it ramps up to $100 50 years from now. And so that can take many different paths, but there's a certain path that it takes so that the model actually says, okay, in 2100, we reach RCP 4.5. We reach this particular forcing based on how much the carbon costs, because the cost of the carbon then drives the profits and the trade-offs between different technologies and different demand and supply scenarios, which really dictate how large the emissions are over the period. Does that make sense?
What carbon price framework are you using?
It's the one intrinsic to the global change analysis model. And so it's basically, I don't know. I'm not familiar with like what are some of the options?
ICN Nordhaus type.
Oh.
Social cost of carbon, like I don't.
No, I
don't really know how this works.
Sorry, it's a carbon tax. Right, so it's basically saying this is a tax on carbon per unit of emission, essentially.
And is that based on like the EPA social cost of carbon, or do you know? Because those things have like order of magnitude uncertainty.
Yeah, it's not a social cost of carbon per se. It's basically like if you're emitting X amount of CO2, right? Your profit margin, and you say you're a power plant, your profit margin is X. But if that, you put a 1% tax on that CO2, right? Then your profit goes down. And so you're less.
Right, and I understand that, but I'm saying, how is this carbon tax calculated?
It's solved. I mean, maybe I don't quite. It's solving for it every time step.
Oh, cool.
Yeah. So basically the way that GCAM works is that it solves all markets to equilibrium, all the energy markets, all the agricultural commodity markets.
Okay, yeah, that would be a way to go, yeah.
Yeah, that's how it is. Okay, now I think we're on the same page.
And I'm impressed.
Yeah.
One more question.
Okay.
Actually, somebody else.
Yeah, and then we'll come back to you. Is that right? Yeah, in the back.
Thanks for the nice talk. I was wondering if there's things in the historical record that you think this model should simulate to help validate that the feedbacks are appropriate, or if there's some sort of constraint to make sure you're producing the right amount of corn or whatever thing that you think it should do right.
There are two distinct answers to that. So the human model is calibrated to historical data up to 2015. Right? So it actually runs from 1975 up to 2015 to align all of its prices and values and production with existing data. And so we're starting off at a point in the human system today to the best of our ability. And then we move forward. In terms of historical runs of this, GCAM itself has had a couple of tests doing hindsight type runs. It does okay. The challenge is that it's a partially equilibrium model at 5-year time steps, and so it doesn't capture a lot of shocks in the system. But general trends are consistent in terms of its agricultural production over the historical time period. In our previous iteration, we did try running it. We wanted to try to run it historically, and it was computationally we couldn't make it work. We didn't follow through completely with that, but it was extremely challenging because in running GCAM historically is also difficult because of the way it's calibrated during the historical period. It sucks up all the data you can find, and so there's also kind of a tautological kind of comparison in a way. So, well, yeah.
I have a question regarding the workflow. It seems that currently you run the GCAM first, and then the E3SM. Is there any effort to make them run simultaneously, or there's no need? Or
Okay, sorry, I wasn't totally clear about this. So step 1 and 2 are getting the scenario set up. And then when we do run them together, so the system does run simultaneously. And so GCAM is actually running with E3SM every 5 years. It's the first thing that runs every 5 years, and that generates 5 years of land use and land cover, and the next, essentially, well, it does create the next 5 years of CO2 emissions as well. In this example, that wasn't passed, but it's doing, instead of projecting 100 years, it's projecting 5 years. And then in 5 years, it gets back these terrestrial productivity feedbacks and then does a new projection for the next 5 years.
okay, so it does coupled together.
Yeah.
You can have your another question.
All right, thanks. I'm just wondering how fine scale you can resolve. For instance, if we deploy a hydrogen hub in Southern California, and then we have measurement from that facility as an example. Would that be accounted for, and there's a pathway to incorporate that, or you can actually provide the actual emissions in some way, and then for you guys and couple models in the near future?
Well, and that depends on GCAM development as well. And so any of that information will have to go into the actual GCAM development structure and system to be represented. And to the extent that that makes a difference is then to be determined. There are, and this is the global version, there is a US version that it probably is more pertinent to, where there's more detail in the US that GCAM runs. And we haven't tried to run that with E3SM.
Thank you, Adam.
While you're pulling up the slide, I'll do kind of the introduction. Yeah, just to reiterate, again, this Human Earth Systems Science Group is just obviously very interested in the carbon cycle. So we care about how the carbon is cycling throughout the whole Earth system. So all different flavors of it. And, carbon emissions go in and out of the land. Obviously, carbon emissions and sinks go in and out of the ocean. So the ocean biogeochemistry is extremely important. So that's why I'm introducing Kat Smith, who's from Los Alamos, from LANL, and she's really helping us to improve our marine part of the biogeochemistry. And you're also a physical oceanographer, physical and marine BGC. So thank you, Kat.
Okay, so I'm Kat. I'm going to talk about the marine BGC, which includes the ocean and sea ice components of BGC. It's a fairly small team at LANL that works on this, and most of us work the majority of our time on the actual physical components of the ocean and sea ice, so very little of our time actually goes into the marine BGC, but we're doing our best. Okay, so you might ask why. So this is going to be a general overview talk of like marine BGC and a little bit of how it's incorporated into E3SM. I'm not going to do any config options or things like that. We're not going to go into that detail. So why does this matter? Well, as we were saying, because of the global carbon budget, the ocean actually takes up anywhere between 20 to 35% of our anthropogenic CO2. So if the ocean wasn't there, we'd have a lot more CO2 in our atmosphere. So it's pretty important. The way it does that, it's through what's called the solubility pump and the biological pump. The solubility pump is basically the carbonate chemistry that's happening in the ocean. So CO2 enters into the ocean, it hydrates, and it turns into bicarbonate and carbonate, and therefore lowers the standing concentration of CO2, so more CO2 can go in. And then the biological pump is through ocean phytoplankton and sea ice algae. Okay, so large-scale features in the ocean and sea ice BGC are influenced by a number of things, but you can see here, so for instance, basically they're not uniform, right, throughout the world's oceans. Air-sea flux, you can see in general, there's outgassing in the tropics, and then you've got downwelling that's happening in the North Atlantic or the North Pacific that's then bringing in CO2 into the ocean when you form the deep water. And then same with nitrate concentration. Nitrate is an important nutrient for the biology. It's not uniform across the US. It's not uniform across the global oceans. In fact, most of the oceans in the surface, it's pretty depleted. It needs to somehow get up into the surface of the ocean from depths. And same with oxygen, it's not uniform. And then there's lots of different things that influence these patterns, like for instance, biological productivity, which is going to either use or create some of these biological processes or tracers. You get export and remineralization of organic matter. So you may know we call this marine snow. It's basically dead animals or dead phytoplankton and their poop and things like that, and it just rains to the bottom of the ocean, or it gets remineralized, etc. So that contributes to these patterns. Advection and mixing, so the physical processes that are actually happening in the ocean and sea ice have a huge effect on these patterns. Many of the gases that flux into the ocean, not just CO2, but there's DMS and other things like that, they're temperature and salinity dependent. So those distributions also affect the biogeochemistry. And also you can see the breakup and melting of sea ice as well can help, because that either blocks or allows light to enter the ocean, which biology needs to grow. In addition to this, there's things like the river inputs that would put in nutrients into the ocean. There's oh gosh, now I'm blanking on a bunch of them. But there's a bunch of other things that affect the BGC, and not just these things here. Okay, so in general, Earth system models have a couple of different ways of modeling the biology and the chemistry in the ocean. So this is not specific to E3SM, this is just general. So with biological modeling, you can either go on the simplistic side with something called an NPZD model. So N would be some kind of nutrient, Z would be a zooplankton, P is a phytoplankton, and D is detritus. Detritus is like the poop and the dead stuff that's floating down. And the reason why we care about that is that often contains carbon in it. And so that is how you export or sequester carbon into the ocean, in the bottom of the ocean. So there's lots of different iterations of this type of model. You can get ones that have multiple nutrients, multiple phytoplankton, or they don't include detritus, etc. But it's the most simple type of model generally that's in ocean models. And it's solved as a system of reactive tracers evolving as just ODEs, right? And then the other type is you can go much more complex, which is what we call a phytoplankton or plankton functional type. And so this is groupings of different phytoplankton and zooplankton based upon their functional type. So we have one tracer that represents all of the nitrogen fixating type biology and all the calcifiers or something like that, right? And then we might also break them up in terms of their size classes as well. You know, different size zooplanktons will predate on different size phytoplanktons. And again, these are solved in the same way as reactive tracers, evolving in a system of ODEs. Often these models separate out the different nutrients. So you have explicit nitrogen, phosphate, iron, silicate, and then it also often breaks it up into dissolved and particulate versions, because dissolved tends to just passively float around, particulate sinks to the bottom. and then also organic and inorganic, because that is important for remineralization. Okay, so you might ask which one of these is better. So an MPZD model, if it's being used in one particular location, it actually does a really good job, despite the fact that it's quite simple. But for Earth system models, we want to go with a more complex model, because even if they're tuned for one specific location or only a few locations, they actually tend to do much better throughout the entire globe. So for most of Earth system models, they use plankton functional type models. And then for the chemical modeling, pretty much all of them do the exact same, all Earth system models pretty much do the exact same thing. CO2, when it hydrates and turns into bicarbonate and carbonate, happens pretty quickly. It's within a couple of minutes time frame, probably less than that. And so for most Earth system models that have time steps on the order of like 30 minutes to an hour, that's practically instantaneous. So it's really just solving a system of equations that are in equilibrium. And I'm not going to put up the equations for that. That seems a little bit much for you guys to, absorb, but you can go and look up those equations. For the most part, most Earth system models, it's the same equations for all of them for the chemistry. Okay, so where does the ocean and sea ice BGC sit in E3SM in particular? So you've seen this component map for most of E3SM. And basically the ocean BGC and the sea ice BGC sit within the ocean and sea ice. They are not their own components. The ocean BGC is its own it's a submodule within the ocean, and the sea ice BGC is just implemented straight into the sea ice. And so any coupling that they do, so there's fluxes between the atmosphere and the ocean and the sea ice and the ocean, those that's all done through their respective ocean and sea ice components through the coupler. So if you're looking for the ocean BGC or the sea ice BGC, they're going to be in the respective MPAS ocean and MPAS sea ice folders, right? Okay, so a little history or overview of kind of the different versions. So one thing I want to point out, V3 for the physical model of E3SM has been tagged and released. V3, but for each version of that, the BGC often gets a next tag. So we call that V2, V2.1 or V3.1, et cetera. V3.1 for BGC is not released and finished yet, so it's still kind of in the process. I know that's a small detail, but it might be helpful for you guys to know. Okay, so V1 for BGC, the ocean BGC, we used a model called BEC, which is the biogeochemical elemental cycling model, I think. And V2, we switched to Marble, which is essentially, it's BEC. So BEC is what's used in CESM, and it's used in a few other models. We switched to Marble, which is basically a modularized version of BEC. So it allows us to add or remove different types of phytoplankton and zooplankton, which is kind of a nice feature. For V3, we're adding a bunch of different things like, in particular, iron dust deposition, which is really nice because iron's a limiting nutrient for a lot of phytoplankton. We're adding in new improved nutrient river fluxes. There's now a flux of alkalinity between the ice and the ocean. And then we have different diffusivities for the BGC traces versus the temperature and salinity. And this might be going over your head, but if you have questions, I'm more than happy to answer them. For the sea ice BGC, for all versions of the model, it's the ZBGC model. And just to note, sea ice BGC is pretty rare in most Earth system models. Most Earth system models do not have sea ice BGC, so we're one of the few models that does. For V2, we added some dissolved organic nitrogen cycling and a few other nitrate and DIC tracer type things. For V3, we're also adding the same iron and iron dust deposition and black carbon deposition, as well as some radiative feedbacks from the chlorophyll. Okay, so a little bit of detail about the two different models. So marine Marble, which is the marine biogeochemistry library, again, that's the ocean BGC. It is one of those functional or plankton functional type models. And here's a nice schematic of it. I'm not going to go into the detail of it. But basically, it's meant to be a flexible type model where you can add and remove species of phytoplankton and zooplankton. And it's also independent of the ocean model. So this is also in CESM as well. As I said before, it's solved as a system of coupled ODEs. The current version that we're using within E3SM has 32 different species, which incorporates both the biology and the chemistry. But this can be changed. It's currently not an easy thing to change in E3SM, but in V4, when we change to the Omega model, it should be a much easier thing to change, that you could just turn on and off certain things. And so the tracers are solved in this kind of format. Basically, there's a tendency that it's solving for, and it's just the sum of the sources in the sink. So an example here is a phytoplankton. This is generally what they would look like. You'd have some kind of sources so that you'd have a nutrient limitation, a light limitation, but that's proportional to the current phytoplankton concentration. And then you have some kind of loss or sinks, so grazing and then mortality. And then in addition to that, through the ocean, it also takes in the atmosphere, rivers, sea ice, and benthic fluxes. And then it also takes in temperature, light, and salinity from the ocean. And something to note is that it's solved on the same grid as the ocean physics. So when you go in and look at output from the BGC, you'll use the exact same grid information from the ocean for the BGC. And in general, it's adapted using a flux-corrected transport. Okay, little overview of the sea ice BGC in E3SM. It's a little less complex, but it's the same kind of plankton functional type system. It's solved on 8 vertical grids, which is distinct from the physics grid, which I think is 7 vertical levels, I think. Yes. And so that's a little bit different. So just something to keep in mind. It also takes in light, temperature, salinity, various different things from the sea ice around it. So it interacts with the physics grid for the sea ice. In terms of how those tracers are transported within the ice, it's broken up into a mobile fraction and an attached fraction for each of the tracers. And so the mobile fraction is controlled, its movement is controlled by internal brine dynamics. So this is the mushy layer type stuff that was talked about yesterday. And then the attached ones are just fixed positions within the ice column. And then how they move from mobile to attached is proportional to sea ice growth and melt. In addition to that, it also does absorption and desorption at the brine interface. So this is fluxes to and from the ocean, and it does this for all the algal and chemical species. Okay, so then this is how they're coupled together. And they're doing this through their respective ocean and sea ice components. There's full two-way coupling between them. They flux various different nutrients and chemicals, and then also the phytoplankton. So I cross out phaestus here. The sea ice model still has phaestus, but when we moved from BEC to marble, phaestus kind of went away. And you may be asking, why do I care about that? It's a phytoplankton that's important for DMS production, which is an important aerosol. So for the most part, those fluxes between the 2 different components are determined in and past sea ice, and it's based upon ice growth and melt, snow loading, brine expulsion, and then obviously the respective concentrations of those 2 different tracers in each of those components. Okay, so I'm going to go a little bit into the results with marble. So the ocean BGC data, it's generally outputted as 5 different diagnostic output levels. So when you say, I want diagnostic output level 1, you get a whole chunk of output, right? And then level 2, you get a whole nother chunk of output. And it's kind of ordered in terms of what your highest priority things to look at are. By default in the BGC comp sets, levels 1 and 2 are on, and that's, for the most part, that's probably all you need. For most of the stuff that you might look at. And then again, by default, everything will be put into the monthly time series, the monthly average time series for the ocean. So they don't get their own output files, they just go into the ocean output files. But if you wanted to, you could alter the streams files and things like that to have higher output frequency or something like that if you really wanted to. There is a small amount of ocean BGC that's in the MPAS analysis package. I believe we're going over that later. But it just includes a few sea surface tracers. So various different nutrients and things like that that we have observations that we can compare to. So observations in the oceans are limited. They're even more limited for biogeochemistry tracers. So that's one of our biggest things that limits us in terms of analysis packaging. But in general, there's also lots of other things that you can look at in there that are not a part of the MPAS analysis package. So you can look at the CO2 flux, you could look at iron deposition, you can look at primary production, and there's a whole slew of other things that you could look at if you wanted to as well. In terms of performance, we do pretty well. So we can look at the top row, that's the CO2 flux in E3SM versus a data product. And you can see in general, we get the right patterns in terms of outgassing and uptake. The same with the DIC, that's dissolved or inorganic carbon. That's important for the carbon cycle. And again, we're getting generally the large scale patterns. And then in terms of time series and CO2 flux, we're doing pretty good. There's a few improvements that we could do. I think getting some more downwelling and deep water formation in the North Atlantic would probably really help us with that. So, okay, moving on to the sea ice BGC. Again, the data output is put into the same monthly files, but for the sea ice, so they don't have a separate output file. And then currently there's no sea ice BGC in MPAS analysis. It just hasn't been, again, we're a pretty small team and we haven't gotten a chance to put it in there, but at some point, hopefully it will. But there's lots of different things that you could look at. There's a lot less output for the sea ice BGC than there is the ocean, but there's at least many of the things that you might want to look at. So like nutrient uptake in and out of the sea ice, as well as primary productivity. In terms of how we're doing, V1 was kind of a little bit outside of the estimated observational range, but V2 is doing a lot better, and we're hoping to see even more improvements in terms of V3. Okay, so that was kind of where we're at in terms of the BGC of both of those components. And then these last couple slides are just showing some exciting developments that are coming along. So the next thing that we're putting in is a benthic model. This is being done as a part of the Interface project, which is an E3SM ecosystem project. Basically, in the Arctic, most of the biology is largely benthic controlled. So benthic means it's at the bottom of the ocean. So these are clams and other microorganisms that are living at the bottom of the ocean that the walruses or other things might feed off of. But in general, as sea ice decreases, we think this is going to change more into a pelagic type system. Pelagic meaning it's actually floating around in the water. And so a key question for us is how is this actually going to change the Arctic carbon cycle, which is important for the whole global carbon cycle. So we're currently developing a benthic BGC submodule. Hopefully that will be online soon, but yeah, so that's really exciting. I'm not going to go into the details of it. Another thing that is coming with V3 is that we have an improved river spreading distribution in the ocean. So originally in V1 and V2, all the rivers were spread the same amount according to a Gaussian distribution with the same exact length scale for all rivers based upon the Amazon, what made the Amazon most stable. And so obviously you don't need to spread all of the rivers this way. And so in V3, we'll have it so that they're proportional to their maximum runoff flux in the data, as well as the local grid scale. And so that helps reduce the spreading of each of those. And this is happening both for the physical variables, so the freshwater flux, and also the nutrients. And then the last one that I'll talk about is iron dust deposition. So there's iron dust in the atmosphere. The ocean and sea ice haven't really historically done a lot with that yet, but it's a critical micronutrient for phytoplankton for growth, especially in the Southern Ocean. And so V2.1 or V1 and V2 use just data iron deposition and then a constant dust iron solubility map. So in V3, those are changing. We're actually going to pull dust and iron from the atmosphere that's actually being transported around, as well as a variable dust iron solubility map. And I guess that's it. Yeah.
You mentioned there's diffusivities different to those of temperature and salinity in the model. For carbon in particular, where does that come from?
Where does the diffusivity, like, how do we determine what the diffusivity is?
Yeah.
That's a good question. I think currently we have evidence to support that the diffusivity for the biological tracers definitely is not the same as temperature and salinity, but we don't know what's the most appropriate value at the moment. I think that'll still, in fact, I do some of this research, and I think that's an open question that we still need to figure out. What we put in the model is the capability to at least have different ones for each of them. Yeah. Yeah.
I remember there is no feedback in E3SM version 1 and version 2, but the chlorophyll distribution can influence the physical, the ocean EGC can influence the physical state, like the chlorophyll distribution influence the SST and the short wave radiation. So is there any improvement in the version 3?
Yeah, so currently in V2 and V1 and V2, you're correct. There is no physical feedback between the biogeochemistry and the ocean or the sea ice. And what you mean by that is you can have self-shading, or you can have where there's so much phytoplankton at the surface of the ocean, the radiation cannot go deeper and it heats the top of the ocean, things like that, right? So you can actually have physical feedbacks. Georgina, we're doing
that. Yeah, so version 2 actually has the hooks in it.
Okay.
They at least do it rudimentarily, but it hasn't been turned on yet, and that's something I'm working with Matt Waltrude on doing. And let's see, the hooks that are there are to actually take climatological chlorophyll maps and to use that, because so right now it just uses a standard water type. We're like, okay, we're at this point in the ocean, I'm going to assume a Gerlach 3 or whatever to attenuate the light. So the first step is going to be to actually, so the hook was put in there a long time ago by Luke from Rickle, but has never really been used. So our step 1 is to turn that hook on and to use the climatological chlorophyll. And then we're actually, now we have Marvel sort of working nicely. We're going to get feedback between the ocean and the simulated chlorophyll at every kind of step. So hopefully within the next year or so. That's pushing for us.
So answer is yes, it's coming. Yeah. Yes.
Curious what nutrient profiles might look like. Is there like a nutrient maximum, subsurface nutrient maximum?
Yeah, I guess that kind of depends on where you are in the ocean. Yeah, there's definitely, I don't have any profiles off hand in terms of.
You do see that features.
Yeah, we see subsurface chlorophyll maximum, subsurface nutrient maximums, things like that. Those features are less prominent than, say, for instance, if you were to do it in an LES model or regional scale model, just because of some of the physics. But yeah, we do see that. So, yes, yeah.
There was an equation you showed that had the limitation of nutrients and light and mortality. You also mentioned there's like 32 species considered. Are there like predator-prey dynamics that are taken into play between all the species?
So not a ton. So
well, we only have one zooplankton.
Yeah, so we only have one zooplankton. They're all just infected passively throughout the water column. And so it's a proximity thing, and it's based upon, relatively simplistic grazing models. You can definitely get more complex than that. The problem is this is 32 species alone is not, and the physics or the biogeochemistry that goes along with it is not a cheap thing to have. And so add any more complexity that you add adds more computational cost. Yeah, so it's fairly simplistic in terms of its predator prey type.
Yeah, and I think because it's DOE driven, their interest is the carbonate and the chemistry. So E3SM's DGC model is very detailed in terms of like the biological chemistry. And so historically, they don't care about fish because that's Noah's realm, and so they don't. So the zooplankton is essentially the closure term, and we don't have a lot of zooplankton.
Though that is changing. The DOE is
It's
starting to get
definitely
interested in fish stocks because of food security. It's an important thing to the DOE now. And so we are going in that direction in terms of higher trophic levels, but it's more likely probably going to be done in terms of porting it to another model that then does the higher trophic level type stuff. Yeah. If that hopefully answers your question.
Yeah, thank you.
Yeah.
You mentioned that you account for the different sizes of the plankton.
Yeah.
Do you also account for different shapes?
No, because we just model them as Eulerian tracers. There's no we're not explicitly, they're not Lagrangian little particles or anything like that. Yeah. Mhm. Yeah.
I wanted to make sure I heard you correctly when you said that, I didn't mispronounce this microorganism. Fastus was being removed.
Faestus, yeah.
Fastus. Are there other species then that would be also still producing DMS?
Not within marble, yeah. I think we would like to have that back in there, but the manpower to put it back in is just not there right now, and it's not a super high priority, but it is definitely on our wish list. Yeah, so there's currently nothing there right now. Yep.
Okay, thank you, Ed. Yeah, we are about very well on schedule. So by now we have concluded the overview for all the component and feature development for the models. So thanks for all the lecturers that come out, putting another effort to prepare and make themselves available to come here to present. Then let's thank them all again. And we are going to go to the lunch break right away and just say this afternoon from all these model simulations generate huge wealth of data. And this afternoon we're going to have more hands-on practicum, in particular the post-processing workflow. With this huge amount of data, that the thing can make our life easier and more enjoyable. So we'll see you return back at 1 o'clock.